Ladies and gentlemen, we will now begin the Nobel Prize Dialogue Tokyo 2025, entitled The Future of Life. First, as a representative of the co-organizer, Mr. Sugino Tsuyoshi, President of the Japan Society for the Promotion of Science, will offer his opening remarks on behalf of the organization. Mr. Sugino, please.
Good morning, everyone. It's a great pleasure to welcome you all to the Nobel Prize Dialogue Tokyo 2025. I'd like to warmly greet everyone here at this event. It's my great privilege to extend a warm welcome to Her Excellency Victoria Lee, Ambassador of Sweden, and Her Excellency Dr. Abe Toshiko, Minister of Education, Culture, Sports, Science, and Technology, along with all distinguished guests. In organizing today's event, we have received warm cooperation from the Nobel Foundation, as well as from the Nobel Prize Outreach, led by Ms. Hanna Stjärne, Executive Director. We would also like to express our sincere gratitude to various companies and organizations involved, especially our event partners, Shimazu Corporation and Mitsui Fudosan Residential Company Limited. The Nobel Prize Dialogue is a wonderful opportunity for the general public to understand various values in science and technology through the dialogue with top researchers. I am very honored to host this dialogue again and to invite outstanding 23 speakers featuring 8 Nobel laureates. Today, we use many technologies that were just dreams before. However, it's also true that we are facing various challenges as a result of advancement of science and technology. I hope today's dialogue will inspire each of you on science, technology, and our future. By the way, we call this event the Nobel Prize Dialogue Tokyo, but is this really Tokyo? No, this is Yokohama, precisely. As you may know, Yokohama has the oldest international port in Japan. So I believe Yokohama is the most suitable city for this event, which brings together the brightest wisdom from all over the world. And the port is really attractive, isn't it? I'm very happy to see so many young faces in the audience today. You may be the ones who realize future technologies that seem like dreams today. And those who are not so young, including me, let's try our best. I hope you will have a fantastic time in the Nobel Prize Dialogue Tokyo 2025. Thank you.
Next, Mrs. Hanna, Executive Director, Nobel Foundation, will offer her remarks on behalf of the Foundation. Mrs. Huene, please.
Your Excellencies, Nobel Prize laureates, speakers, ladies and gentlemen, friends and colleagues, Welcome to the Nobel Prize Dialogue in Tokyo 2025. Japan has a proud history in science, and we're very happy to be here for the 6th time. Over 1,000 people or organizations have received the Nobel Prize since the first award in 1901. And 3 months ago, we celebrated last year's Nobel Prize at the award ceremony in Stockholm. And for the first time, artificial intelligence was recognized. It was a historic milestone in both physics and chemistry. And in economic sciences, the prize was awarded to economists providing new insights into why there are still vast differences in prosperity between nations. The Medicine Prize recognized microRNAs that are proving to be fundamentally important for how organisms develop and function. In literature, as you know, Han Kang was awarded the Nobel Prize. She's the first person from South Korea to receive this honor. And the Nobel Peace Prize was awarded to Nihon Hidankyu, the survivors in Hiroshima and Nagasaki. We live in turbulent times. Major issues are being discussed on a global level, and the outcome is likely to affect us all. And the vision of Alfred Nobel, the inventor of the Nobel Prize, was to recognize remarkable achievements and those who have contributed to the greatest benefit to humankind. For almost 125 years, the Nobel Prize has highlighted the importance of knowledge, the importance of science, of culture, of peaceful solutions, and today we need that more than ever. For many Nobel Prize laureates, the search for more knowledge about life itself is a question that keeps them up at night and that drives their research forward. The question of what life actually is has eluded humans over the centuries, and many milestones helping us to know more have been awarded the Nobel Prize. Today, we will learn more about how science and technology, combined with a better understanding of the world around us, might change our lives in the future. And many of you who are here in the room are students. A special warm welcome to you. Nobel Prize laureates again and again emphasize the importance of students. The future is in your hands. And we hope that you will be inspired to choose a career path in science that might lead to very concrete and groundbreaking findings that can improve our lives in the future. I would like to thank JSPS for the excellent cooperation, President Sugino Tsuyoshi, as well as the team working behind the scenes. And I also would like to thank the next Minister Abe Toshiko. Nobel Prize Dialogue Tokyo is organized by Nobel Prize Outreach with the support of Nobel international partners, ABB, EQT, Scania, and Stegra. And a special thanks also to the Embassy of Sweden in Tokyo. And finally, I would like to quote the medicine laureate from 2001, Paul Nurse. He said, "We need to care about and for life on our planet. To do that, we need to understand it." Thank you.
Thank you very much. Next, Ms. Abe Toshiko, Minister of Education, Culture, Sports, Science and Technology, will offer her remarks. Minister Abe, please.
Distinguished guests, ladies and gentlemen, I'm Abe Toshiko, Minister of Education, Culture, Sports, Science and Technology of Japan. I'm very pleased that this event is being held with the participation of so many eminent guests. I believe that remarkable achievement of Nobel Prize literature relates here today a result of their overcoming numerous challenges from a young age, ultimately pioneering a new field of research. These groundbreaking accomplishment has not only opened up new frontier, but also built the foundation for the future. A cutting-edge technology are transforming our society, like rapid development of AI and science and technology are becoming more and more inspiring the link to society. Our ministry next will continue strengthen the effort to support young researchers who are shaping the future through the science and technology, and to foster inspiring research environment that encourage groundbreaking discoveries. Let me conclude by expressing my sincere appreciation to the Japan Society for the Promotion of Science and Nobel Foundation for their effort to hold this valuable event. Thank you very much.
Next, we invite you to enjoy a taiko drum performance by Dako-on. Dako-on is a creative wadaiko drum group based in Yokohama, Kanagawa Prefecture. They perform in a variety of venues as a group, contributing to the local community. With the theme, Seeing the Sound, they aim to bring smiles, energy, and strength to as many people as possible through their heartfelt taiko performances. They have won numerous taiko competitions, including the World Top Taiko Competition and the National Championship. Please enjoy their performance.
Good morning, everybody. How lovely to see you all. My name is Adam Smith, and it's my very great pleasure to be your guide to today's Nobel Prize Dialogue. As you see, we'll be considering the future of life, and in particular, how science and technology might affect life in the future, and how we can get the future we want from science and technology, and perhaps avoid some futures we don't so much want. As usual, our dialogue will be a series of panel discussions mostly, bringing Nobel laureates and international and local experts together in conversation to expose us to a variety of different views and hopefully make us all think. Now, we know how hard it is to know what will happen in the future. And so we thought we better start with a discussion about the challenge of prediction. And for that discussion, I'm delighted to bring together three people. Two Nobel laureates, Ada Yonath, who received the Chemistry Prize in 2009 for unraveling the structure of the ribosome, and William Phillips, who received the Physics Prize in 1997 for trapping atoms with light. And also Maki Kawai, who is president of the Japanese National Institutes of Science. So please join me in welcoming them all to stage. If you'd like to sit at the end. Bill, please, in the middle. And wait for it. She's coming. Please do sit down. Make yourselves comfortable.
Thank you.
Thank you very much indeed. Let me just see if I can help. Do you want a hand? Do you want a hand? Do you want a hand? Okay. Please welcome Ada Yonath. So, Ada, I have a bad back today, so we're both pretty slow. What can I do? It's lovely to have you here. It's lovely to have all of you here. So let's just start by how hard it is to predict the future. Ada, your work unraveling the structure of the ribosome took an awfully long time. Did you have an idea of how long it might take and what the results might be?
Honestly?
Yes.
No.
No.
I hope that I can progress the knowledge. I did not really expect to solve all the problems, the entire problem.
So you set out on a problem you didn't think you were actually going to be able to solve?
Well, I didn't think that. I didn't predict myself to solve, but I thought that I will provide the world with the tools that could be used for solving.
So you...
And I thought that if I'm young enough, and I was at that time, maybe I will reach it myself, but I couldn't even dream about it.
Well, that's interesting. So you set out on a course hoping that you might get somewhere, you might help along the way, but not knowing exactly what the result will be.
So, if I knew the result, I didn't have to work.
Quite so. Bill, if we you work especially with quantum mechanics. If we turn to quantum mechanics, there's a field where no one ever predicted what the future might hold.
Yes, I think that's right. Well, this year, as you know, we're celebrating the International Year of Quantum Science and Technology. It's 100 years after the beginning of what we now call called quantum mechanics, with the development by Heisenberg of matrix mechanics and Schrödinger of wave mechanics. But thinking about, if you'd asked this question, this kind of question, to people like Heisenberg and Schrödinger, what will quantum mechanics lead to? I'm sure they would have given answers like, well, it will help us understand the structure of atoms better. We'll understand something about the structure of molecules better. We might even be able to learn a little bit about how chemistry works by understanding things at the microscopic level. I cannot imagine they would have predicted mobile phones, that they would have predicted the entire range of semiconductor electronics that we have today that has transformed the lives of almost everyone on Earth. I can't imagine they would have been able to foresee that. In my own experience as a boy, I can remember people that predicted by now all of us would have our own personal rocket ships and we would commute to work using them. No one was thinking that we would have the ubiquity of computers, everyone having many computers in their own home. As late as the 1980s, there were computer companies that said there is no reason why anyone would ever need to have a computer in their home. And that company, of course, went out of business. But they were so wrong about the predictions. And I've seen it again in my own career, for example. I would say all the things that were important that came out of the work that I've done were things we did not anticipate.
Okay. Ada, please.
If I'm allowed to add a few sentences, the ribosome, the body I was working, the internal complex.
Sorry, Ada, you've just lost your microphone.
I lost my microphone. Oh God.
Here it is. I think if you just hold that. Just hold that. If you can carry on speaking if you just hold that. Oh.
And this, by the way, is why I always refuse to use that particular kind of microphone and have one clipped onto my tie. Just saying.
I think it just raises the challenge of prediction. Who knows what's going to happen, right? Even in the next 1 minute. So what are we doing here, trying to talk about the whole future? While Ada's putting her microphone on, Maki, would you like, you have an overview of all of science with the Japanese. You have an overview of all of science from the Japanese Institutes of Science. So would you like to talk about just, historically, the challenge of knowing what is going to happen?
Okay, so at the moment I'm serving as a president or manager, I would say, to cover the 5 institutes for the natural sciences, including Astronomical Observatory of Japan and some of the molecular science and physiology and basic biology. I remember when I think it was in 2017 when Osumi-san got the Nobel Prize in biology field. He worked a long time in one of my institute. And people were so surprised. They were not at all ready, meaning that predicting somebody to get Nobel Prize or somebody to get a super result from science, the prediction is very, very difficult. And what we all know is that we need to have various science, the basic science, to be ongoing all the time, even though we do not know what will come out from this field. And so looking for the variety of fields in natural sciences, I would say that don't focus too much. We have to believe our belief in science, the scientists' belief, and let them go. So that is what I think the most important thing to encourage the natural sciences. I hope I'm answering to your question.
Absolutely, you're answering. Beautiful. Thank you very much indeed. Ada, now you're back.
So if I am allowed to add a little bit, ribosome is a particle that Many of it belong to every living cell or animal or a butterfly, whatever. Whatever has to live has to have a ribosome that reads the nucleic acid instructions, the genetic instructions, and produces proteins according to it. As I said, it has about 100 components. Few of them were known when I started, not all, but it was known that they exist. And how they function and how they exist and how they are packed was my problem, was the aim of my studies. Since very, very good and known scientists tried to do it before me and failed, I thought that if I also fail, it's not so bad. I will be as good as those that already did not reach it. But if I expected to move a step or a few steps further, it took 20 years, but we solved the whole problem. And it's correct for every living cell. So I'm very proud of it, but it's not my pride that matters, it's what it added to science. And since then, several groups, several institutes went into studying other larger proteins, larger ribosomes, smaller ribosomes, ribosomes of bacteria, ribosomes of elephants, and there is a lot of progress in this matter. I don't think I have to give a lecture now about all what you do with knowing the ribosomes, but at least ribosomes are known.
Thank you very much indeed. All three of you have set the scene very nicely, that basically you need to allow basic science to flourish in all sorts of different directions, and it's hard to predict when things will be known, and it's hard to predict what the benefit of knowing those things will be. Nevertheless, those that are providing the science funding and society in general wishes to get results from it. They wish challenges to be solved. They want to move forward. So there has to be some kind of roadmap and decisions about what gets funded and what doesn't get funded. And this also fits very much into the challenge of prediction. So, Maki, would you like to start? I mean, you do need a roadmap for funding. You do need a roadmap for science. How do you create a roadmap against a backdrop of basically not quite knowing what's going to come to fruition, what's going to be successful?
I would say that roadmap should be, necessary, but it shouldn't be so strict. And the portion between the basic science part and the focusing part is very important. And to my understanding, I think if you want to have a fruitful harvesting, for instance, you're not just putting some seed to a specific place, but before that, you have to make a soil comfortable to grow the plant. Maybe you need to bring in the water. Maybe you have to structure the land. So these kind of basic environmental structuring is very important. Maybe science is not equal to the agriculture, but I think it's quite similar, that we have to have a reasonable environment, reasonable condition, and reasonable people to work in this society. And so preparing for this environmental issue is the most important thing. And then the second important thing to look into the roadmap is you have to look into the people who is making growth a little bit quicker than the other. Then you can just push a little bit to these areas, but don't forget to feed the other area simultaneously, because that will be the next harvesting candidate. So writing a clear roadmap for what comes next is not easy. But to have these kind of structured roadmap consideration I think that is quite important. The people usually, especially in our country, people are eager to catch up the other countries. We are very good at looking something to catch up with, but we are not very familiar with lead the community. So if you come to close to the top, the people start, let's see, this is quite good. So let's look for something that is not good yet. So every time we think that somebody is coming to the top is not sufficiently feeded, but somebody behind has will be the winner of this roadmap. And this is not good for Japanese point of view. And I would like to encourage the Japanese people how to make a realistic roadmap that will push the top of the top to the top.
The analogy of, if you like, tending the garden is a really beautiful one for nurturing science. Thank you very much indeed. Bill, would you like to comment on this?
Yes, well, I think that you've articulated very clearly the importance and the challenge of figuring out how to fund science. And you have to have support for fundamental science where you have no idea what the results will be, because if you don't fund those kinds of things, long-term progress will never happen. And you also have to fund near-term problems where it's clear that you need solutions to these problems now. And I'm troubled to think that perhaps the best way of doing that is to have people in charge who have vision. Now, the trouble is that's a very difficult thing to guarantee, that people should have vision. In the United States, there is a committee on science as part of the Congress. And in the room where they meet, on the wall is written, "Without vision, the people perish." So somebody had enough vision to write that on the wall. Now, whether you can learn how to accomplish that, I don't know. My late, great laboratory director, Catherine Gebbe, was the overseer of 4 Nobel Prizes in her organization during a relatively short period of time. And people often asked her, "What is your secret?" And she said, "Hire the best people, give them the resources they need, and get out of their way." Now, a lot of people will say that. She actually did it.
Please, Ada, yes?
So I'm trying now to say, why did I go into this area or this field that was known to be impossible? It's because I had a problem, I had an accident, it doesn't matter. I found a pamphlet of one of the air companies that says that they are going to the North Pole in the winter. That this was their, the name of this of this article. And they say that in the North Pole, in the winter, there are no life being evolving. The bears are waiting for the summer in order to make families.
The polar bears.
The polar bears, of course, in the North Pole. And I thought, why does it happen? Because I had time, I had my accident, so I had time to do less active work. I thought that this happens because in the winter, the chances of staying alive of the little babies, if they are made, are very low. So the bears are already stopping the production of the new little bears. And then it was correct. I found out that if I take any cells and cool them to -10, -5 degrees Celsius, the cells stop growing, but they don't die. They stay. So I thought this is what the bears are doing in the winter. But I didn't really want to work on winter bears and killing bears in order to understand ribosomes. This was too much. I looked for other conditions. In Israel, there is a sea that in Israel it's called the Salty Sea. In the world, it's called the
Dead Sea.
The Dead Sea, yeah. It's not fully dead. There are two types of bacteria living there, but they don't function very well in this salty water, and I thought I should focus on them. It's much easier than bears. I don't have to wait for winters and so on. And this was the way to go.
It shows that inspiration comes from everywhere in the garden. You never know where the ideas are going to arise from. So it's in research, you have to keep everything flourishing.
Yeah.
Yes.
Another thing that I think this shows is that you often learn something new when you go to the extremes.
Correct.
That's what you were
Correct.
looking for.
Then afterwards, after a few years, or over 10 years, I went to atomic piles and went to the sewage of the atomic piles and found bacteria there that I could stop its growth and look at their ribosomes.
Life everywhere. Bill, everybody's outlining a very lovely scenario for science where you let things flourish and you get out of the way of good people and just hope it will happen. But actually, that's not how it happens. I mean, the National Academy of Sciences produces 5-year plans. And,
yes.
So how do you square the desire just to let it all be and the need to direct?
Yeah, well, it's a difficult thing. You mentioned the National Academy of Sciences coming up with these often reports. We do them every 10 years. I've been involved in a number of them. We've never been able to predict the most important things that were going to happen in the future. But that didn't mean that we didn't have some perspective about what was hot, what was developing. It's just important to understand it's not the whole picture. So I guess the answer is you do the best you can. You're not going to do a very good job of prediction, but that doesn't mean you shouldn't try, because you need to give some direction, this kind of flexible roadmap that you've described. It has to begin someplace.
And what about the desire for society to see things solved, to see a result from the science? I mean, Maki, you know, people are clamoring for solutions to problems now.
Yeah.
What would you say to people who say, come on, where are the results?
I think this is my understanding. The social problems are quite clear, but the way how to solve this is not seriously determined. There are many routes of solving things. And of course, science and technology can contribute to the solving these problems. But I think the new invention is somehow a little bit more deep, and it does not come directly to the social solution, but it grows to become one of the solutions. So if we want to solve the social problem immediately, what science and technology can do is, to my understanding, there are many known science and technologies. And in order to apply these science and technology to the solution, I think we need to think about how the private sector or government will choose the answer. Sometimes it costs a lot. And if you just think about cost performance, they just throw away, and then some of the solution may be not resolved. And so we have to be very careful. The scientists can give some answer, but what to select and what to put into the social activity is somehow the governmental or the private sector's people's decision matters a lot. So up to some point, we scientists can contribute, but finally, I think the decision of the government or the decision of the private sector, whether this pays for the human beings, or does it pay for their benefit, and they think they have to choose.
time goes quickly. We have just a short time, so Bill, please.
I think it's really important for scientists to tell the stories. In addition to saying how wonderful our latest results is, it's a good idea for us to tell the stories. It's one of the reasons why UNESCO declared the International Year of Quantum Science and Technology, to give us a chance to emphasize the stories about how basic fundamental research led to wonderful results. One of the stories I love to tell is about how when Einstein's theory of gravity came out, it was declared that only 3 people in the world understood it. If the engineers who developed the satellite navigation system had not understood it, it wouldn't have worked. So something that was completely useless 110 years ago became essential to something that we use every day.
It's such an important point, and it's something we will come back to later, especially in the afternoon, this idea of bringing society with science, the smooth communication of what is happening at the bench to society at large. It's such an important point. Thank you very much indeed. Ada, I'm going to turn to you for a last comment. What do you think people should bear in mind today as they think about how science and technology might change life? That's a big question, Philip.
It's a big question. The answer is even bigger and not known to me. but on the surface of it, scientist that has an idea which is not completely crazy, only partially crazy, should be acknowledged and maybe even addressed and supported.
Thank you very much indeed. Thank you to all my panel. It's been a joy talking to you, and to start this conversation off today. Thank you.
Thank you, Adam.
Okay, so now may I help you get up? Do you want to?
I can get up. I can try.
As I said, most of the day is devoted, please, Maki, thank you very much indeed. Thank you. By the way, this is Ada's daughter. Most of the day is devoted to panel discussions such as you've seen, but we do have the occasional talk. And next I'm delighted to introduce Svante Pääbo, who was awarded the 2022 Nobel Prize in Physiology or Medicine for mapping our genetic origins and how we related to those species that came before us and then disappeared, but with whom we interbred to a certain extent. And so who better to give us a talk about where we came from? So please join me in welcoming Svante Pääbo to give a short talk. Thank you.
So, Your Excellencies, ladies and gentlemen, what I then wanted to talk to you about is sort of not the future of life, but the past of life, or at least the past of modern humans, if you like. And just as an introduction, let me point out to you that if you study genetic variation in humans from all over the world today, what you find is that most genetic variation can be found in Africa. And if you look at all variation that is outside Africa, that's less than what you find inside Africa. And that's surprising because there are, of course, many, many more people living outside Africa than inside Africa. And the interpretation of that is that modern humans, the ancestors of everybody alive today on the planet, evolved in Africa, lived there for a while, accumulated genetic variation, and then a part of that variation went out and colonized the rest of the world. And with genetic tricks, we can also figure out approximately when that happened. And that was very recently. Modern humans, well, maybe 200,000-300,000 years ago in Africa, and less than 100,000 years ago, more like 60,000-70,000 years ago, they started seriously colonizing the rest of the world. But they were not alone at that time. There were other forms of humans around in Africa, and outside Africa, in Eurasia, in Western Eurasia, those modern humans that came out of Africa met Neanderthals, and in Eastern Eurasia, Denisovans, distant relatives of Neanderthals that lived in this part of the world. So those Neanderthals and Denisovans are the closest evolutionary relatives to everyone alive today. So that's sort of the basis of our big interest in it. We are interested in how we differ from them, what makes us special, and in the question why we are here today and they seem to have disappeared. So if we want to ask those questions by genetic means, what we need to do is retrieve DNA, genetic material from old bones that are at least 40,000-50,000 years old that look like this. And the technology for that is then what we have worked on over the past couple of decades. You sequence lots of short fragments from such bones, match them to the human genome, and start reconstructing how the genomes of those other forms of humans looked like. And that then allows you to, when you compare it to further out groups such as the great apes, you can see things that we share with the Neanderthals, that changes that happen on that common lineage. You can find things that are unique to the Neanderthals and Denisovans, and those things that are unique to modern humans. So that's one cool thing with having these genomes of our closest relatives. Another insight that came from that was that if we look, for example, on one chromosome here, chromosome 9, in different individuals, each line is an individual, we find big segments of tens of thousands of nucleotides that are identical or very, very similar to the Neanderthal genome. And that then indicates that when modern humans met these Neanderthals, they had babies together, and some of those babies were successful enough to contribute to the genes of people today. So variation came over from these Neanderthals and exists in people today. And you find this contribution everywhere outside Africa. It adds up to, in each individual, to 1 or 2%, but different people carry different parts of it. So around 60% or so of the Neanderthal genome is still present in people today. So if you like, they're not totally extinct, they live on in many of us today. But so we can then perhaps come back to the question, why are we here and not Neanderthals or Denisovans? And there are 4 sort of speculations about that I wanted to bring to you, maybe as a basis for a discussion afterwards. 4 speculations about why modern humans made it and not these other forms of humans. And one is that there are many evidences suggesting that modern human population sizes were much larger than those of other forms of humans. You can see that here. You see present-day Africans have more genetic variation than people outside Africa, as we said. But Neanderthals and Denisovans have even less, suggesting that their population size was smaller. There's also archaeological evidence suggesting that if you look at how many archaeological sites there are from late Neanderthals or early modern humans, there are more such sites from modern humans, and they seem to have been used more intensely. And modern humans, of course, spread to many parts of the world where these other forms of people never came. They spread to Japan, they spread to the Americas, to Australia, and so on. So one part of why we are here and not they may simply be that we were more numerous and absorbed these other forms of humans into our population, so their sort of morphology disappeared, if you like. But there are other things one can note also. For example, that cultural and technological evolution seems to accelerate with modern humans. At least from 70,000 years ago or so, technology becomes regionalized and changed rapidly, whereas Neanderthal technology was very constant over even hundreds of thousands of years and homogeneous over their entire range. An expression of that, perhaps, is that projectile weapons, according to many people, seem to have come with modern humans. The earliest bows and arrows may be in the order of 60 or 70,000 years ago in Africa, and then become very numerous with modern humans. And finally, there is also more subtle sort of changes, perhaps, or which suggest that symbolic thinking, or at least art representing things, comes with modern humans. There are things that are suggested to be Neanderthal art because of old dates, but that art, sometimes I joke and say that looks like very modern art because I can't see what it depicts. Whereas figurative art comes with modern humans and become quite frequent in many parts of the world. So how are we then different from Neanderthals? Maybe is there even a biological basis for an ability to accumulate culture and develop it rapidly? So we are particularly interested now in these changes here that are unique to modern humans, because we think that among them there may be some hiding that may have to do with this ability to become very numerous, develop technology and culture and so on. So we can focus on these things, make catalogs of those things, and they are in a way then a recipe, a genetic recipe for being a fully modern human. And those changes are not very numerous, in the order of 30,000 or so. We will look at things that exist in almost everyone today and was not there in Denisovans or Neanderthals. And we are particularly interested in things that may affect how the brain works or develops. And in our group, we focused initially now only on changes in proteins that actually have functions in our bodies. So there are about 100 such proteins. We've studied a dozen of them. I just want to hint at one example of this. This is this enzyme here, an enzyme in energy metabolism that it is studied together with Wieland Huttner's group that are experts in neuronal development. And what we then do is to change in stem cells this change in the protein back to the ancestral state, and we can then differentiate those stem cells to brain organoids that are sort of little mini brains that mimic early development of brains, and then compare the modern human version of this with the ancestral version in the developing brain organoid. And we can then look at these stem cells that divide to make neurons in our brains, and we find that we've ancestralized this, we actually make slightly less of these stem cells. And there seems to also have effects in that if we look at the neurons that are formed, there are also fewer neurons. So where we are at this point, this is sort of the big question in the room, is neurogenesis different in modern humans from that of Neanderthals and Denisovans? But there are things, sort of caveats to think about in this. One is that we here study very early brain development, that those changes may be compensated later and not affect the adult individual. Another caveat is that I think that many interesting features will be affected by many different genes. So single genes may not give the full story. And another caveat is that when we now learn more about genetic variation around the world, we find that many ancestral variants actually exist somewhere in the world in present-day people, either because they survived over hundreds of thousands of years, or because we got them as a contribution 50, 60,000 years from these ancestral groups. In this case, when we look at sort of a small group in Africa and one in the Philippines, we actually find that many of those genes on our list exist in rare individuals today, and some are not so rare. For example, this change in this enzyme here actually exists in almost 30% of individuals in this African group. And since it's on the X chromosome, around 30% of males actually carry this ancestral variant. So does this mean that this is an uninteresting change in our gene? I don't think that that's necessarily the case, because I think to end here we can take a step back and think about how we define Neanderthals, for example, from the morphology of their bones. They have a number of features, sort of a round skull, a sort of big eyebrows, an occipital bun, for example. But you can find people alive today that have just as big eyebrows as the Neanderthals had, but they will not have all the other features. So it's a combination of features that make us say this is a Neanderthal. And similarly, if you look at skeletons, it's a combination of these features that make us say this is a modern human and not a Neanderthal. And I think in the end, probably this will be true also for the development and function of our brain or our metabolism, that a view of what makes us modern from a biological perspective may be that we carry many or most of these changes in their modern human form, but none of them is in themselves necessary to be a fully modern human. The question that we then struggle with is, of course, are there some of these that are particularly important, particularly fundamental, or even crucial? And that is sort of the billion-dollar question for the next few years. So this work then goes on in Germany, in our group there, and also here in Japan, in Okinawa, at the Okinawa Institute of Science and Technology, a small group there. And with that, I then thank you for your attention.
It's fine. So, and Svante, the audience may indeed be interested to know that you're an adjunct professor at OIST as well, and you're going down to Okinawa after this meeting, isn't it?
That is right, yes.
So you've become part Japanese.
Yeah.
Very nice indeed. Yes. Please, thank you very much indeed. Thank you. Thank you. It's so important to consider what it means to be human as we consider how science and technology will affect us in the future. And again that comes up in conversation. And so now we continue with that question with a panel discussion. This one will feature Hiroshi Ishiguro, who's a professor from Osaka University, known to you all, I'm sure. Juichi Yamagiwa, who's the Director General of the Research Institute for Humanity and Nature in Kyoto. Rich Roberts, who was awarded the 1993 Nobel Prize in Physiology or Medicine for the discovery of split genes and is now Chief Scientific Officer at New England Biolabs, where he's been for a long time. And this one will be moderated by Juleen Zierath, who's Professor at Karolinska Institutet. It will also feature a surprise guest, but I will allow Juleen to introduce the surprise. So, I think we're pretty much ready. So if the panel would join me on stage, please. Please, come on. Thank you very much indeed. Mr. Yamagiwa. Thank you.
Well, we are going to talk about a question that has really occupied the minds of so many individuals in so many disciplines. What makes us human? What does it mean to be human? And Rich, I'm going to start with you. You know, as a biologist, what does it take?
Well, I think if we look back at our origins coming out of Africa, clearly there were animals living there that were not human. Okay? They're apes, various gorillas, all sorts of things. And so I think one of the things that really differentiates us from the bulk of the animal kingdom is the brain, and the way in which the brain dominates our lives, allows us to do things often that we shouldn't do, but nevertheless gives us some feelings for the rest of society, for what we might do to control them, to help them, or whatever. And I think this is something that is distinctly human as opposed to other animals. So for me, that is one of the things that really stands out. And one of the things I like about it is it can make us very creative. We can ask questions, we can try to find out how things work, what they work, and as a scientist, that is what I love to do.
And we got a taste of that in Svante Pääbo's lecture as well.
Right.
And Juchi, you were a primatologist.
Yes.
And you take another perspective, perhaps. You know, you're working with primates. Based on that background and comments from Rich, what do you think it means to be human?
You know, the first feature appeared in the human evolution about 7 million years ago is bipedal walk. And the human brain started to increase in size about 2 million years ago. So 5 million years, our ancestor just walked bipedally with very small brain. And then, why and how human brain increase in size? That is, you know, social brain hypothesis proposed by Robin Dunbar, a British primatologist, and estimated that, you know, brain size increased with increase in group size. So that is social brain. Our brain increase the size to adapt the social complexity. So maybe about, you know, from 2 million years ago, human ancestor increasing group size and to interact complex, social structure. So that is meaning the size. But Svante proposed us in the content of the brain in modern humans. So I don't know exactly what happened, but not size. In the contents and the direction started to evolve.
So we hear a lot now thematically about the brain and also about creative art. And Hiroshi, I would like to ask you a little bit. You think a lot about this, I think, what makes us human and what makes us so special.
My view is more extreme in some sense, right? So why we have this kind of a big brain, how we can use this big brain, right? So that is the technologies. So I really think no, we cannot clearly define what human is, right? But we can say that human is different from animal because we can use the technologies for.
To help us there, do you think we should introduce our special guest?
Okay.
So we do have a special guest, and so I'm going to let you make the introduction to our special guest.
Okay. Well, today's I'm bringing my copy. He has my knowledge, and he can, he can have a conversation with the student and the guest, right? And actually, I am building a pavilion for the expo. On the Osaka Kansai Expo, I'm building a pavilion, and he will welcome you. Right?
I'm not sure of can everybody see our guest? All right, well, we do have but we can talk to our special guest.
Yeah.
And perhaps maybe we might want to ask our special guest a few questions. There he is.
Well, you can.
Who are we seeing here?
May I speak?
You may.
Hello? Can you hear me? Hello? Hello, can you hear me? Hello? Hi.
Could you clarify what you mean by it?
Well, who are you?
Let me see. I am Hiroshi Ishiguro, a university professor and researcher. I explore human nature through humanoid robots. How can I assist you today?
Well, please explain your expert area.
Could you provide more details about the police or the export area you're assigned to? It will help me offer a near wave of response.
So, what are you doing in a university?
I'm my university, I conduct research on humanoid robots to explore human nature.
Okay.
My work involves understanding interactions between humans and robots, and creating robots that closely resemble humans.
Should we have any more questions?
Well, I think it's okay. Well, the people, please visit the third floor. He is waiting for you, and you can have a conversation with him.
All right, so here's your chance. How about a round of applause for our special guest? That's great.
Let's see.
All right, thank you. Bye-bye. All right, so we still haven't solved the question. We've got some insights. I mean, being human really is genetics, biology, culture, it's consciousness. Can we create that in a robot?
So
It's open, yeah, all three
Okay.
of you. You might have different opinions about that question.
Right, probably. Well, I think it's a challenge, right? So, so far, I was trying to develop the very human-like robots, and then clearly the bottleneck was conversational functions. But thanks to the large language model, we could develop the, pretty good conversational functions. It's almost human-like. But however,
Almost, you said.
Almost, not perfectly. But however, we are feeling some difference between the human and the robots. That is a consciousness, I think.
Mm-hmm.
So we cannot feel the human-like consciousness through the conversation with the robots. So how we can do that? Still, this is open questions. But on the other hand, right? So, and we can enhance. I have two approaches. One is to develop the fully autonomous robot. The other is the teleoperated robots, right?
Mm-hmm.
So if we use that kind of technologies, and for developing the avatars, teleoperated robots, so we can enhance our abilities of the conversations, right?
Mm-hmm.
And if we use that, the technology for enhancing the human abilities, so I think we can have more, how can I say that, more better jobs, right? So I think that is the kind of way of human evolution. So that is the difference from an animal.
All right. He had the word almost in there, and I don't know if either of you want to comment on the idea of almost. Can these machines really be human?
I think for me, one of the things is we can certainly write programs to run machines. They can do a lot of very clever things. But can they ask good questions? Can they ask the really insightful questions that we as humans can ask when, I want to know, how does your nose work? How does your hair work? How do your fingers work? And to get into the details of all of that, is it going to be possible for robots to really take over and ask these questions and get insightful answers that are useful for us? Or is it just going to be an exercise in asking questions, getting results, but then no action afterwards? Mm-hmm. And so for me, I like the idea of curiosity, finding out how things work, and then seeing how we can use it in some productive way.
You can go ahead and respond to that, because I think that's one you were struggling with as you're developing this.
It's quite difficult, right? Human is so complicated. When we are just simulating the, some possible part by using AI, right? So, my interest is to compare the robots and humans and try to understand what is the humanities, what is the important aspect of humans, right? So I think that this is a very interesting tool to understand humans, right? So that is my feeling.
I think it's fun, but whether you're going to understand much about us or not, that I don't know. As I say, for me, it's sort of asking questions, getting results, and then seeing where that can take you, allowing your creativity to take over and say, oh, I've made this discovery, but I could use it in this sphere that I've not even thought about before. Mm-hmm. I'm not sure that robots and AI are going to be able to take us there. Maybe I'm wrong.
Go ahead.
I think your model, your robot, can approve Turing test. I don't have time to explain Turing test, but
maybe you should explain what the Turing test is.
Okay, Turing test. If AI or robot is covered with the box and invisible. And human asks the question, and robot answers the question. If human can't understand that is a robot or human itself, that is approval of Turing test. So your Android can approve the Turing test.
While still we need to limit the condition and the situations, right? So, and then, you know, the most important thing is the time, how long that we're going to have a conversations, right? So if we have a longer conversation, of course, everybody can find that is not humans. But for the, you know, very short time, and then maybe the elderly, the young children, some, you know, if they don't know the much knowledge about the humans, so we may cheat them, right? So,
from my experience to talk with gorillas in the wild, we don't need language. Facial expression and, you know, attitude that can have some meanings, and we can understand with each other. And there is some ambiguity, but we can, you know, omit some ambiguities.
Well, that's the emotion coming through, isn't it, really?
So emotional, you know, conversation that you Android can clear that kind of, you know, ambiguity.
Well, I think right now we are focusing on the multimodal processing, multimodal the perceptions and the representations. So that is a difference from the previous robots, right? But however, it is not so easy. So we need to develop the very sophisticated body mechanism and sensations, right? So we need to do the many things, right? But, you know,
how far are we from building in consciousness and emotionality into these kinds of robots?
Well, I'm not sure, right? But I hope that we can do it within, the 20 or 30 years, right? But every year, we are improving the technologies and improving developing so many sensors, so many, the tools, right? So that some days, I believe that we can do that, but not today, right?
Yeah, I have a question. If you had two robots, couldn't they have an intelligent conversation?
Well, so
does that? Yeah, at least we can do that with three individuals, right?
You know, depends on the definition of intelligence, right? So for the simple conversations, but maybe, you know, it's a level of intelligence. I really think so that, right? So large language model and AI is, in some sense, they are so clever, right? Comparing with in some average knowledge and the intelligence of a human. But of course, if we compare with the top class people, right, like you, of course, you know, when we can, they cannot. They find ideas.
I'm thinking, you know, you have two robots. They start talking. What are they going to talk about? And are they going
somebody
to
needs to
go
kick it off.
beyond whatever was the initial thing they got started?
So you know, my imagination is, it sounds like a kind of reinforcement learning, right? So I just remember the AlphaGo. AlphaGo is, you know, searching. It's a kind of a random search. So if they talk forever, right, they may find some solutions, right? So that
or
we
not.
cannot find.
I think, you know, until modern human appeared, evolution proceeded interaction-based, you know. So brain size increased in more complexity of interactions. But after the appearance of modern human, and knowledge-based intelligence developed, and with the aid of science and technology. And now many information, the evolution of information are now bringing us that's much more complexity of integration of information for decision making. So our brain cells did not respond to such kind of request. So we just rely on AI or some you know, outside our intelligence, I guess. What do you think about that?
Yeah, well, you know, when you look back and you say, well, as humans started to develop and got smarter, one of the things they did was to be creative. They, instead of being gorillas and going out and looking for, you know, whatever food they could find,
for example,
they started farming. They realized that you could bring some of these plants in from the wild, put them in your backyard, and grow them. And I think it is these kinds of traits that, for me, define being human. Being able to adapt, being able to improve your environment, improve what's going on, and then to share that knowledge. And I think this is really crucial to being human, personally.
May I comment on that? Right. So, you know, the AI.
So you think your robot can farm?
Well, you know,
it's okay. Go on.
Right. The robot and AI is going to be a part of our partners. I mean, so today everybody using AI. And we are using a lot of robot technologies in the factory, in many places, right? So, and AI and robots can enhance the human abilities, enhance our brain activities. So we need to coexist together, right? So that is, you know, the human future, I think.
Well, clearly we're not going to go back because we're here, right? And we're in a world where we're embracing more of this kind of technology. So what do you think are some of the ethical considerations that we need to take into, take on?
Yes, of course, right? So, well, and always, so when we develop the new technologies, you know, we have two possibilities, you know, to use in good way and bad way, right? So we need to have a better moral to use the more powerful technologies, to use the AI and robot technologies. I don't like to use my robot technologies for the military purpose, right?
I think that, you know, the essence of humanity is still empathy, sympathy, compassion. And, you know, it's expressed by, human attitude, like your android. But now, invisible things appear in many informations, and we can integrate more information into ethics or logos, and to rely on the future figures. So that is very important, but it's very difficult for us, human body, express our empathy, sympathy. That's our human body.
Well, and some of that's learned experience, but also that can be wired in our genetics. You know, a lot of these things that make us really unique are wired in our genes. So just thinking a little bit more, we're living with these technologies. What do you think some of the ethical considerations are from your point of view as a biologist?
Well, I think for me, the ethics of all of this is who is going to control the robots? Are the robots going to control us? Are we just generating a set of autocrats? Or are they going to be there to help us? And I think I very much agree with what you're saying. Empathy, compassion. Almost all humans are compassionate. You know, if you're a scientist, you can go anywhere in the world, meet another scientist, you've got a friend. We start talking, we can disagree about things, but we don't find it necessary to shoot one another to show who was correct. And I think this idea of being peaceful, of having empathy, of thinking good things about people is something that we really need to make sure we don't lose if we start to use AI in the wrong way. And how we do that, I don't know. But, you know, if there's a gene for autocracy, I say we find it and eliminate it.
Yeah.
All right. Well, what do you think the next big steps are going forward?
So, transhuman. Transhuman. So, I would like to ask Ishiguro-san, after completing your android, but it is not biological things. So, what do you think in the future? Android is also physical matter, or by providing some biological component with the android?
Well, I am not a specialist for the biologies, right? So probably my way is to use the AI and the robot technologies for making a kind of a copy of the humans. But the important thing is how we can define the humanities, right? Even if we don't have, the robot doesn't have any, the biological stuff, right? Robot may have a human right in some sense, right? So that it's a matter of a society. So how we can get the human rights? Always society will give a human right to the people and to the animal and to the robots, I think. Right, so and I think it depends on the level of intelligence of humanoid robot.
Well, that theme comes up a lot, the societal experience as well,
Right,
and how that
right.
feeds into this. It's certainly a big biological component, a genetic component, but a lot about how we're experiencing the world. And whether we can teach all of that to a computer would be, I think, the big question going forward.
I'm sure we can do it. The question is, will we?
We already
it can
are
be done.
working on it. How many people here use AI? Just a show of hands.
Everybody, right?
Oh, many.
Look at that. And how many people use things like ChatGTP?
Everybody.
That's right.
Right, the human totally.
You mean cheat GTP?
Well, there's so much information out in the world that it is really a challenge to have it all. And sometimes having it quickly is a matter of life or death for some people.
Right. But the problem is with programs like ChatGPT is they are trained on data sets that are not necessarily all true. And I think one of the problems I see with AI is we need to make sure that the training sets we use contain facts. They don't contain mistruths. They don't contain incorrect information that's put out there deliberately.
Well, you said already early, asking the right question is very, very important. And then having sort of a knowledge base to be able to ascertain whether or not the information you get back is fact correct or not.
But I mean, ChatGPT doesn't care. It just goes for whatever literature it can find and then produces an answer.
It's always very polite.
400 years ago, René Descartes has already predicted the modern world. I think, therefore I exist. And thinking agent has no body, and body itself is a material and following the physical formula. So that is modern world, governed by artificial intelligence. Artificial intelligence has no body. So in the future, if we rely heavily on AI, it is the world proposed by Descartes.
I think a lot of the whole ideas around these humanized machines is really our quest to understand what makes us unique and what makes us human. And clearly there's a lot of efforts on way to try to understand that. We heard a lot about the brain and how important our brain is. Cultural experience is really big. The ability to have a consciousness and empathy are also factors. And we were told in the opening remarks to dream big. And so we'll see where this goes. But as I see it, it's a conversation to be continued throughout the day. So thanks again to our colleagues here. And we should all think a little bit about what makes us special and unique as humans. Thank you very much.
Thank you so much. We gave you an enormous topic to tackle, and you took us a long way and have introduced many themes that will be red threads throughout the course of the meeting. So thank you. And I'd like to remind you that the robot version of Hiroshi Ishiguro, our special guest, is available to talk to throughout the meeting. So in the breaks, please go up to the 3rd floor, and you'll meet him in a booth, and you can please just go and have a chat. Now we're coming on to a section that we've called Challenges, and we're introducing some of the problems that we hope to tackle with science and technology. First of all, we're going to have a conversation about diversity and inclusion, and I'm very pleased to introduce Chieko Asakawa, who's director of the National Museum of Emerging Science and Technology, Miraikan. So please, if I may ask Chieko to join me on stage. This one, the other way. Thank you very much indeed. Chieko, welcome. And I had the enormous pleasure of visiting your museum yesterday in the company of Bill Phillips.
Yes,
and
thank you very much.
We met a lovely group of high school students who asked truly insightful questions. So it was wonderful. Thank you. So diversity and inclusion is a particularly hot topic in certain regions of the world just at the moment. But we're not going to encompass the whole topic. How would you define diversity and inclusion as we're going to discuss it now?
Okay, great. Thank you for the great question. So I believe diversity is not something special because everybody is unique and different. But sometimes, the differences are so large. And however, as I said, diversity is a natural part of who we are. So that's why it is essential for us to understand it and recognize its importance. And as we all know, I hope, a diverse team can be more creative and can be more and more innovative. And I've been experiencing it so many times. And maybe I can give some examples later. And as for inclusion, if diversity is advanced, the advancement of inclusion will be automatically achieved. And technology is going to be a key or one of the major factors to drive inclusion.
Thank you very much indeed. And of course, you have your own personal story of tackling the question of inclusion. Would you like to introduce the audience to that?
Yes, sure. So in the mid-90s, I developed the IBM homepage reader. It is the first practical voice browser in the world. It has developed first in Japan in 1997 and later supported 11 languages. But when I started developing the homepage reader, researchers around me, they are mostly geeky, scientific guys. And they never thought the web is going to be to listen. They thought the web is going to see. But I argued. I'm here, and I can tell you what this web page is talking about by just listening. And they were, persuaded. They understand it. And just, a couple of months later, we developed the homepage reader. It is because, the team was diverse. We can make the difference. That is one, great example for me.
So the home-based reader, what was your own personal motivation to move into this area?
Oh, thank you for another great question. So it is really related to my personal experience. When I was 11 years old, I hit my eye on the side of a swimming pool. And at that time, I wanted to be, by the way, an Olympic athlete, not a scientist. But anyway, after many bumps and tours, I joined IBM Research. But anyway, when I lost my sight at the age of 14, I lost my independence as well. And there were two major obstacles. The first one was losing my the challenge of information accessibility. In those days, there were no personal computers, no internet, no smartphones. I'm very sure many young, people in this, here, they don't understand what such
what a world without these things is like, yeah.
So anyway, I couldn't access any information by myself. That is about the information accessibility. And another difficulty was mobility. I couldn't go anywhere by myself. So I lost, information accessibility and mobility accessibility. So when I became a researcher in IBM Research in 1985, I found the power of technology. And I thought in the future, our life is going to be changed. So I started working in the area of accessibility, and in 1990s, I could develop the homepage reader. That is a kind of historic.
Thank you very much, Chieko. If I may ask you, it must have taken enormous personal resilience to get through that time when you were 14.
Okay, yeah, many people ask me about it, but I always say, I always forget something painful. So I'm pretty optimistic. However, the thing I remember very well was because in those days, our society was not inclusive. It was very difficult for me to be included. So there was no way for me to go to public high school in those days. So the only option was for me was to go to a school for the blind. And I really felt, I'm excluded. So I thought in the future, I want to open up my life to be included. So I wanted to find a new type of job as a blind person because I didn't depend on something that was provided by others. That goal really encouraged me to keep moving forward. So inclusion, if in those days our society was more included, maybe I may not be here.
Well, yes, it's certainly driven you in a wonderful direction. And yesterday at Maraikan, you introduced us to this extraordinary new piece of technology, the AI suitcase that you've been developing to help people navigate the museum. Would you, and other things, would you like to introduce us to that?
Sure. The AI suitcase is now we are developing with Miraikan. And by the way, Miraikan is a National Museum of Imaging Science and Innovation located in Odaiba, Tokyo. So if you have a chance to, after this convention seminar, please visit us. We'll be ready to welcome all of you. And by the way, another thing is we have 29 messages from Nobel laureates. And yesterday, Bill Phillips one was added as a 29th message from Nobel laureates. So if you haven't come to our museum yet, please join us tomorrow.
not just a message, even a question posed to the next generation to solve, yes.
Yeah, that is a question, sorry. Thank you very much, Adam. Okay, so we are now developing the AI suitcase. It's a navigation robot for the visually impaired. And maybe people may wonder why suitcase shaped. I travel a lot with white can and a suitcase. And at the airport, I noticed that just a regular suitcase is going to help me navigate at the airport without a white can. So one day I thought if we can integrate perception, control, planning, and AI into the suitcase, it can be my new travel companion. And it was like 7-8 years ago. But now we have, the latest AI and robotic technology. So we are moving very quickly the past few years. And can I show you that video?
Please, yes, please do. So if we can roll the video.
We arrived at Diversity Tokyo Plaza. Where should we go?
I'm thirsty. Please take me to a place for a drink.
There is a smoothie shop. Would you like to head there?
Yes, please.
We have arrived at the smoothie shop.
I'd like to explore around here. Do you have any recommendation?
There is a life-sized statue of Unicorn Gundam outdoors. It is one of the symbols of diversity.
Sounds good. Take me there.
There is a Hello Kitty shop on your left. Here, they sell sweets shaped like Hello Kitty dolls. They are priced at 600 yen for 10 pieces. Avoiding people. Entering the festival plaza. We have arrived. The Gundam statue is on your right. Be my eyes.
This is a smartphone.
Be my eyes.
Take a photo and it's going to analyze in real time.
Take picture, button. Take picture. Analyzing picture, please wait. The image shows a large, wide robot statue, resembling a Gundam, standing in front of a building. The robot is positioned on the right side of the image, and it appears to be looking upwards with one arm slightly raised. The building behind it has several signs on it. The most prominent sign reads Diversity Tokyo Plaza. Other visible signs include Round 1, Uniqlo, ABC Mart, GU, H&M, the Gundam Base Tokyo, the Super Sports CBO, and the Adidas logo. The sky is clear and blue, suggesting a sunny day.
So much information in a short time. That was a challenge for the simultaneous translation.
I don't think no human can speak
No.
in this way.
So anybody using this is much brighter than anybody normal. This is an extraordinary thing to have.
Yeah.
Does it guide you? So how easy is it to walk with the suitcase and to be guided by it?
Oh, it's very easy. So if, by the way, if you are interested in using it, Expo is going to start next month, 13th of April, and we are going to demonstrate this AI suitcase every day. So please come back to Japan again. But anyway, it's very easy. I just hold the handle, and when I hold the handle, it starts moving.
Yeah.
When I release it, it stops. And when it's turning right, the right side of the handle is going to vibrate, same as left side. So handle itself is very smart. So what I need to do is just hold the handle, release it. And I can talk to a smartphone saying like, please take me to the Ishiguro Pavilion, for example.
So one of the things that strikes me is that this allows you to add extra levels of information to what somebody not using the suitcase would have. So somebody visiting your museum, for instance, could use this to get information that would not otherwise be available.
You mean the without suitcase?
Yes.
Sure, because a suitcase itself is a navigation. It take up the role of the suitcase is a navigation. So in addition to navigating a user to a destination, suitcase, the most important role of the suitcase is navigating a user to a destination. And as for the AI part, of course, we can use AI part, just a smartphone. And so when by the way, museum experience is going to be changed for the blind. Before the latest technology is available, we could only depend on someone accompanying us. So the information is going to be limited by someone. Or long-winded audio description, audio guide.
Long-winded. Yeah.
So you have to type number or QR code these days. But the description usually very long. So if I cannot stand up in front of some exhibition, because it's going to take 3 to 5 minutes, and my friend maybe want to keep moving. So before the latest technology, museum experience really depend on someone accompanying us. But with this kind of latest technology, we can even enjoy by ourselves and get more information. And not just listening to the AI describing about the exhibition, we can ask the AI why this exhibition is good, or why this area is not crowded, or whatever. We want, whatever information we are curious, we can ask to AI. But of course, AI sometimes make mistake. So we human beings need to be smart, intelligent enough to find it out.
Once again, it's a question of coexistence. It's an extraordinary technology, and it's amazing to see how fast things are moving. I'm very grateful to you. Thank you very much indeed for taking the time to talk to us and to introduce us to the technology. And the only thing that occurs to me is that that's an expensive suitcase to lose. One worries about losing a suitcase under normal circumstances, but if somebody stole that, you're in trouble.
That's a great question.
How much does it cost?
Much. Maybe in this audience, many of you are scientists, so they would know how much one LiDAR cost, how much one GPU cost, so you can guess. But I've never thought about losing it.
Sorry.
I will start thinking about it. Thank you. Maybe I can reply to you next year.
Okay, fine. Thank you very, very much. It's been a pleasure speaking to you.
Thank you very much, Adam, and nice to meet you again. Thank you.
Thank you, Chieko.
Thank you very much.
Thank you. Okay. So much to get through. It's lovely. After lunch, as you've seen from the program, we have these breakout sessions where the meeting divides into 2 streams, and we'll talk about 4 different areas of technology. We'll talk about AI, quantum technology, genomics, and sustainability. And you get to choose 2 of those to go to. Now we're going to have a session where we're going to discuss some of the challenges that those different technologies might help solve, and indeed themselves pose. And so for this panel, we've chosen 1 panelist from each of those 4 discussions that will happen after lunch. We have from the University of Tokyo, Arisa Ema and Akira Furusawa, and then we have 2 Nobel laureates. We have Andrew Fire, who was awarded the 2006 Nobel Prize for Medicine, Physiology or Medicine, for discovering RNA interference, and also Ben Feringa, 2016 Nobel laureate in chemistry, for his work on molecular machines. Once again, our moderator will be Juleen Zierath, who you met before, and please welcome them all to stage. Please. Thank you.
Well, as Adam said, this is a bit of a teaser for this afternoon session, and we want to just look at some of the challenges going forward. So maybe, Andy, I'll start with you. And you think about medicine and biomedicine, what do you think are some of the big challenges that we face?
I mean, some of the challenges we face are learning more about how biology works, as Rich introduced it. We have to know how, from the quote from Paul Nurse, we have to understand it. Some of the questions are how to integrate all that knowledge. And, you know, tools of AI will be one of the sets of tools that could be useful there. But I think the other part of that equation is that we have to understand how the tools are providing us the knowledge. And AI is notoriously bad at that. And so if there are future tools that allow us to know how they're working and what data sets they're coming from, that will be beneficial. And how do we make those kinds of approaches and that kinds of analysis sort of feasible for a human being with our sized brains to do? The other thing I would point out is the great fascination with the human brain. It's much more interesting for all the young students there. The human brain is more interesting than any AI to study. And so I hope you'll use perhaps AI tools, but the questions that you may address will be how human brains work either individually or in groups.
Right. You want to respond to that at all in terms of some of these complexities?
Yeah. So I think, you know, using AI as a tool, especially AI for science issue, you know, how to, it's really, you know, promising. And also I think the data set you mentioned is really important because in the medical area, I think there's lots of includes not only like, you know, the research data, but also it includes like a privacy issues and the consent issues. So even though, you know where the data came from, but it includes, you know, the privacy or the personal information, then that is another, you know, ethical concern. So I think it's really very important and it become more innovative, but also we need to consider about the governance issues and the ethical issues as well.
So I might come back to some of the complexities of the brain in a bit, but if we stay on the theme of challenges ahead, Ben, what do you think from your perspective are some of the challenges with, you know, quantum science, nano, et cetera?
Yeah, for me, what is most fascinating about a living system is the complexity and the autonomous functions. Just to give you, I'm a molecular scientist, so we build molecules and materials, and we get a lot of inspiration from Mother Nature. And let's look at one of the big challenges, that we face, how to recycle our materials to make a better sustainable world, because we use a lot. We throw away plastic instead of reusing it. Now, one of the challenges is how to make a strong material that can hold this water, like this bottle, or this material, but also to recycle it on command. This is what your body does. I learned from my friends in biology, but my colleague here can comment, that almost half of your body weight is recycled every day. Can you imagine, ladies and gentlemen, half your body weight is recycled every day? We are not smart enough. We don't know how to recycle our plastic properly, only a few exceptions. We have to learn this, and we have to look at Mother Nature and understand the complexity and the dynamic functions of Mother Nature, and then we will be able to make our sustainable future. Just one example.
Do you want to comment on autophagy? It's a very interesting issue here. We have a Nobel laureate who is Japanese, Oshumi, who received the prize for that. And you say he solved all of this for us.
Oh, our friends in biology, they know a lot about life. And we look at them all the time and get inspiration, you know, and then translate it into artificial systems, of course. Because an airplane is not a bird, eh?
Looks like it, though.
Yeah, but it does not fly like this. You know. So this is why we need to work together.
And so we need to understand the human machine before we can
understand and translate into new possibilities for the future.
Yeah, it's taken a few billion years to evolve all the systems to do that. But
I don't have a billion years.
but I mean, we'll figure some of those things out. But they're going to be challenging and interesting questions that are out there for the next generation to solve. How do we work with our environment in a way that's sustainable? And one of them is going to be recycling and reuse. And learning from biology is good, and maybe using biology along the lines.
Sure.
But if that's a whole bunch of bacteria instead of a bottle, and you drink it, and then you make the bacteria reorganize themselves to a desk chair or a book, that would be great.
Akira, you want to jump in? Any thoughts from your perspective on the challenges here?
I'm working on quantum computing, and a big challenge for us is to reduce energy consumption of quantum computer and also AI. At the moment, everything is digital. Digital consumes a lot of energy. But human brain, or just brain, analog computers without error correction. And the energy consumption is really, really low. For example, in the case of digital computer, for recognition of cat and dog, you need nuclear plant, right? But in the case of analog computer or brain, the energy consumption is less than one piece of onigiri, rice ball. So we should go to analog computing. And quantum computers are inherently analog computers because we have to handle superpositions. So in that sense, we should stick to analog computing with our quantum computer.
Any thoughts around that? Big challenges? We can do a quick lightning round. What do you think the biggest challenge is?
So I think the issue is how we wanted to, in the previous session, like we wanted to understand human being, or how we can live, society in a very sustainable way. And I think AI, genomics, quantum, all those technologies are. We need to consider it as a tool, but also we can also learn from our human bodies and how we can effectively use it. And but in that sense, we can use it in more innovative way. But I am sorry to introduce later. But my specialist is in the social science. So I really respect all those new technology and new development, innovation. It makes our society much more effective, much more better one. But also, we also need to think about its ethical, legal, social, considerations of the impact. And I think the challenge is how we can collaborate together with, social scientists, engineers, or the scientists. So those is, maybe the audience might think, you are the researchers, or you are the professors, so you can collaborate it. But I think even though we are using the same term like AI, genomics, what we think, or maybe human beings, what we think is slightly different, or maybe totally different. So I think this kind of conversation is really important, and that might be the basic challenges that we face. So I really appreciate, what is the the very important topics of each areas and how we can collaborate, or maybe would like to ask you all, so how are you collaborating with the other fields? And that would be the hint for our futures.
I'm thinking, at least in the medical field, we're thinking a lot about what makes us human, and we're trying to understand the human genome, and then we're trying to understand how we can maybe potentially make us better through medicines or genetics. There's also the ethical issue there as well. And I know those fields talk a lot, but I don't know if you want to comment on that. Are we going to be able to CRISPR in the right genes once we know what they are?
I think our biggest challenges are social, actually. How do we generate a group of people that can meet a common goal? And one of the models for that, which works very well, is the orchestra. A benevolent orchestra with a director in front and conducting, and people are working together, playing different instruments and making wonderful music. And then really the best example I saw was the drumming group that just was on stage. They seemed to be working, to me, without a director. Everybody seemed to be working together perfectly and making music and making art. That was tremendous. I think we should understand the neurobiology and social biology of that group, and we'd be a long distance further than we are now.
All right, so that brings in a point that she made up about having different points of view around the table to solve a question, and you would want the drummer there.
I would want the drummer there, and the conductor to understand how they work, and then the back stand of the violin section to understand how they work, too.
Ben, you've solved big, complex problems. What's your perspective on this?
But I fully agree. I think there is a crucial role for the universities that we train our students to look also about cross-disciplines, because it's very difficult to predict what will be the next big development. Did you predict that we would have smartphones, which completely change the way we communicate and run our societies? This is, with all the influencers and so, this is also a big social and communication problem, etc. And so maybe nobody had predicted that. At an early stage, maybe at universities, we should recognize and discuss with our colleagues in other disciplines and train our students, to ask the right questions and so, and be prepared for their role in society. So I'm a strong advocate of this kind of things.
Yeah, I think that's great. I remember my father, when I was young, telling me, he said, Jules, one day you're going to be buying things from a computer. And I was like, Dad, that's never going to happen. Boy, was I wrong. He surely knew. So you have to have this idea to be dreaming, right?
Yeah. Imagine to live without the smartphone. I'm sure when I asked the question here, nobody can imagine that we had
The thing is, probably one day we won't have that. We'll have something else, something bigger than that.
There will be other things in the future.
Exactly.
Talking about robots.
Yeah, for my case, I started to talk to brain science people. As I said, in brain is analog computer without error correction. And the system is just linear operation and plus some nonlinear operation. That's it. So I really build such type of quantum computer because, again, it is analog computer, and also we can make a program for it. So it is controllable. Like her opinion, it is very important to talk between different type of people and to have new knowledge. For us, especially, talking with brain science people is really crucial.
I also have one question that, or maybe also like to ask you. So, or maybe your father. So, where we get this kind of future visionary? So, it's one of the things is that maybe we can talk with the other discipline, and maybe we can have the very different images, or maybe future perspectives. But we are talking about the future society today. So I was just wondering, so is it like a sci-fi thing, or maybe science fiction?
So her question is, where do the visionaries come from?
Yeah.
And are they born, or are they created, or how do you cultivate that? Any thoughts about that? Because you talked about the conductor, right? So if you got the wrong conductor, you could really have a mess. So how do you promote that, the visionary aspects.
Well, the visionaries are born, they're human beings, and they go to the library and they read science fiction. And they learn what people have dreamt, and they start dreaming of their own dreams. And I think that's part of where that comes from.
So you think the imagination of, the other field, or that the people's imagination is really, inspiring your research?
If I may comment on that, I fully agree. I think this imagination and creativity of the young people is the most crucial aspect here, And there is a lot of talk about robots, and artificial intelligence and so. I'm not in this area, but we build materials, and what I'm really interested in is to make hybrid systems. So not so much to create a robot, and if a robot, as Richard mentioned, can have emotions or feelings or whatever, but what will happen, when we implant chips in your brain, when we get more understanding of our brain functions. And I recently heard this lecture about a visionaire, and that was really intriguing. We find it normal that you get a hip implant when you are older and you don't walk properly, or you get a pacemaker or whatever. But to get a chip in your brain to help you a little bit to remember names, or to help you, with all kinds of disabled functions. But then he said, imagine with all these functions, and this integration, they can download your brain content on the internet. So where are you then? In the cloud or in your body? So this is a kind of vision for the toekomst that we should, for the future, that we should also discuss about this potential, Not only about robots, but about the human electronic interface, for instance, or human robotics interface, all these kind of things. Are we hybrid systems in the future? Where are we then?
I don't have the crystal ball. Now, you guys are,
Are we in the cloud?
Yeah.
Some people may, think that is very, utopian view, but some people may see, think of the dystopian world.
I don't know.
Well, I think we talked a little bit about the ethical, considering the ethics as well, and I want to end on that. We have just a few minutes left, so we have the challenges to understand our brains and try to understand how to improve human health is really important. And then trying to cohabitate in a world where clearly in front of us we see a lot of technologies. And sometimes that's blurry, sometimes not. But where will the ethics be on this as well moving forward? Ben, maybe some thoughts, because you raised it with downloading the brain.
I think it is crucial that we discuss also about ethics aspects in an early stage. Maybe if we had done that, but I'm not so much in the genomics area, but if we had done this for genomics a little bit earlier maybe, that the universities were advocating this to contact with our other disciplines in the universities, that the natural scientists, also were much more involved in what are potential ethics aspects. I think it's important, because then bringing the message to the general public and to our politicians and tell them, look, this is pros and cons. This is something we should discuss about, and build then your decisions as politics on facts and not on fiction or opinions, That is I think that is our role, as scientists.
Clearly with the embryonic stem cells, ethics has been a really big part of that discussion as well. But even just making recombinant proteins was a big debate on whether or not you could bioengineer insulin production, and what would that mean. Anything from your point of view in terms of ethics related to the medical field?
I think you get a lot of people with knowledge around a table, and you start to find out what people's concerns and values are. And to me, one of the concerns is sort of the do no harm part of it. We don't want to do any harm with the science that we do. And another concern is that any kind of manipulation of the environment, as a human environment, should support human diversity. That's a very important part of it. And if we're in that realm, we're actually, I think, creating a better world if we can do that. If we're not doing that, we're probably not creating a better world.
Okay,
great. And there's also this aspect, that we should go outreach like we do here now, but advocate to the general public, what the potential risks are. I vividly remember what I read about Henry Ford. People said, about these cars that looked very dangerous when he built the first car. And Henry Ford said, if I would have asked what I should have done, I should have breeded faster horses instead of building a car. Faster horses for our carriages. Then we would not have cars. And the same with airplanes. When the Wright brothers were flying for the first time, what the people said? If God wanted us to fly, they would have given us wings to fly.
So these are the visionaries.
So we have to think about these ethical aspects and how it would, And what are the real risks? It's difficult to say.
All right, so we're going to wind up, but I think messages that we need to reflect on are certainly diversity is important, cultivating the creative mind, allowing people to have what we might consider to be some crazy ideas, because we need the visionaries, and then being in a world where we do have a dialogue and consider the ethical impact and how this might affect us in terms of sustainability. A lot of these things we're going to talk about in the breakout sessions, but thank you so much for your interactions this morning, and I think it's time for lunch. Oh, all right. Or maybe it's time for Adam. We'll see. But thanks again.
Thank you.
Thank you.
Hello, everybody. Welcome back. Nice to see you again. Thank you. I hope you had a nice lunch. Thank you. Thank you, but honestly, I think the applause should be for you, the audience, for being here. It's a Sunday, and you choose to be here rather than elsewhere, and I think that deserves a round of applause. So please give yourselves a round of applause. I think that would be nice. Okay, so now let me invite my panel to join us. We have people you've met before, Ada Yonath, and Arisa Ema, and also from the University of Tokyo, Yutaka Matsuo joining us on stage. So if we could all come on stage, please, that would be great. Thank you. And Ada will be joining now. Hello. Hi. Thank you. Hi. Thank you, Ada. Please do. Now, I have one announcement to make, which is that we were due to be joined by Geoffrey Hinton for this session. And unfortunately, he is, due to unforeseen circumstances, unable to join us. He was very, very much looking forward to joining us online from Toronto, where he lives, where it's now 11:30 at night yesterday. But unfortunately, he really cannot be with us, despite very much wanting to be here. However, I recorded, it so happens I recorded 10 days ago a podcast with Geoff Hinton for our series Nobel Prize Conversations. And so I have some of, I don't want to have them now yet, but not yet. But later, during our discussions, I'll be playing 2 or 3 clips from that conversation. So you will have Geoff's latest thoughts on some aspects of what we're going to be talking about. And what we're going to be talking about is the impact of AI. Of course, it's a subject that's already come up many times during the conversation already. And I think it might be good to break this into 2 pieces. There's been much discussion about the far future possibilities of AI, and we will discuss that, but it's also good to focus on the here and now and the current impact, challenges, and opportunities of artificial intelligence. So let's start there and then move into the further future as we go along. And this is a session in which I would love to have some of your contributions. So at a couple of points during this conversation, I will be reaching out to you to get you to make questions and comments. So we should move quickly on. Right. Let me just make sure my telephone's turned off. That would be bad, wouldn't it, if the moderator telephone went off? So let's focus on current possibilities with AI. Let's start with you, Arisa, if we may. What do you see as the major challenges for AI now that it's presenting to us as humans?
Thank you, Adam. Challenges. I think there's various challenges, like the privacy, accountability, transparency. But I think the biggest challenge is like the challenges to like what is a human being? I think this is kind of related to the morning session. So when, I think many of you actually are using, the ChatGPT or the Gemini or even DeepSeek, and maybe you think it's really very effective, that supports your work or maybe your lives. However, or maybe the research as well. However, so it kind of, questions us, what is our human being's role, or what we can do to, to use that in proper way. So that actually challenges what is our human being's role, or what actually we expect to, for the future society. So that's the biggest question. And with that, under that, I think there also exists some kind of, very domain-based discussion about, the privacy, security issues, safety issues. But I think we need to tackle on this bigger issue first.
And I think lovely you start there. And I mean, one clear example of that being a problem is the automation of many people's jobs. And so many people who are not in any way involved in the development of AI or thinking about AI are finding AI is potentially going to replace what they do. And that's a huge societal disruptor. And I guess that point that they are not involved, they're just experiencing this, is a big change.
I think so too. So this big ChatGPT or the LLM issue actually changed because prior in like 2015 or 16 something, the many discussion about this AI challenges are mostly for the AI developers. But right now, what we are talking is like, the employment, education, or future work, or maybe, what's the human role will be. So, the challenges came to much more, the user-based challenge, user-oriented challenges. So I think this kind of widens, the people who need to talk about this topic.
Yeah, indeed, exactly. It should be a much more inclusive conversation. Yutaka, do you want to comment on this briefly?
Yeah, yeah, I want to mention about the recent advancement of AI. And as Adam said, the automation is progressing. We have AI agent services a lot recently, or we could say agentic AI, which can do things like make reservation for hotels or travels, or do purchase on the Amazon website or something like that. The past generative AI does the conversation. So if we put question, they can give us answer. But what they can provide now is action, the sequence of actions. So they do things for the users. So that's one thing. Another thing is physical AI. So with the advancement of the so-called the robotic foundation model, the robots now have the generalized behaviors, so they can fold laundries, or they can, do the many housekeeping jobs. So now, from now on, maybe the robotic industry will change a lot, and that is happening right now. Yeah.
And in terms of AI agents, of course, they can set their own sub-goals, and that raises questions about what goals they will set themselves.
Yeah, that's true. But currently it's more like a theoretical question. But the reality is we cannot expand the domain where the AI agent will work. So, for example, doing making a reservation or the purchasing something for the user is a good starting point. But if we expand that, then the agent does not work anymore. So now we don't have the level of discussing the sub-goal should be an issue for the human or not. Maybe we are more in a primitive level compared to that. Yeah.
Thank you very much. So much positive and much challenge around this. Ada, do you want to talk about the impact of AI on research at all?
On research?
On research? I don't know.
Really?
Well, I don't know. It's up to you. You work on folded proteins, and one of the major developments in AI recently has been the solving of the protein folding problem for AlphaFold 2 from Google DeepMind. But maybe you want to talk about something else. The floor is yours, please.
Thank you. So proteins are performing almost all functions of every living cell in every living animal, human, bird, flower, anything that grows. Proteins are able to do it, or they are designed to do this by their structure. The structure is accommodating those materials that participate in producing new materials. And when proteins were discovered I don't talk about long ago, but when there was already sequence of protein, sequence of the amino acids that make the proteins, people thought that maybe they can predict what will be the structure of the protein that has to make this and this and this challenges. And I don't want to say they failed. I also don't want to say they succeeded. The success was marginal, very good for the time, about between 15 to 20% of correct prediction of structure, based on the structures that were known at that time, which were very, very few. I'm talking about now 60 years ago or 50 years ago. And the level of prediction was more or less constant with a little increase until about 40–45% of correct prediction. So for the prediction, there was a specific organization created called CASP. They were focusing on a specific protein, which was at that time a subject for research of structure. And in parallel, they wanted to predict the structure. And as I said, there was an increase in the correctness of prediction, but not higher than about half the cases. This was every second year, called CASP, and every second year it was somewhere else in the world. But I thought that 50% correct prediction is fantastic, but Molt, that started this initiative, thought that it should be better. When AI came into the game, then the story changed. But not only because of AI, but also because more structures were known. It means the basis to this type of research became larger, and there was more information from structures that were determined by experiments, crystallographically.
It's very nice, actually, that you emphasize the human component in this, because the story could be told, as perhaps I introduced it, that AI came along and AlphaFold 2, and suddenly we had the structure. But yes, the human effort of the hundreds of thousands of people who'd been collecting structures and depositing them in the protein data bank, and the human success that had happened prior to that goes alongside it. So it's a beautiful example of humans and AI working together, actually.
Yeah, that's the only way structures became part of AI.
Yeah.
Protein structures and also proteins' duties. Performance.
Can I just jump into here? So I think what you mentioned is really important, how AI, the human endeavor to do this research, and then there comes like AI as a tool, and how we can use this technology in very good manner, or maybe, how we can use, correctly as a tool. And my research field is more, how people can use this AI in the workplaces, or maybe in the research area. And what I see is that kind of collaboration is not working well to some extent. In some kind of field. And there's some places where this kind of collaboration works really good, but there's some kind of places that this is actually not working well. And this is not only from the technical limitation, but it's more like how human beings can adapt, or maybe the environment or the readiness towards this AI. So I think what you mentioned is like how human beings or the researchers are actually accumulating data, and how they can use this AI as a tool. But somehow maybe we think that the AI as the very great tool, but the thing is that even if the technology is good, but the people's awareness, or maybe the places awareness, so maybe like infrastructure issues, the networking, the security issue, or maybe how do you say, the data set. If those things are not ready, and I can say that almost many places are not ready yet. Then the implementation of the AI is not going well. So I think we in the short term, what we are actually facing is that maybe we might be expecting too much on technology, but we also need to kind of reconsider our work style, or maybe our awareness, or maybe we can maybe we can adjust it to the AI, but also we can also adjust how AI works. So it's more like a collaboration. So it's not like just implement the technology and everything goes well. It's not like a silver bullet.
Thank you very much indeed. That's a very nice point to open up to the audience. We don't have very long, so if you would like to make a comment or ask a question about this near-term AI, impact of AI, please do so. I can't believe it. Is there a hand raised? I see a hand raised here. Could we have a microphone come down, please? Microphone? I'm told that there are people with microphones running around. They need to run faster. Hello, thank you very much. Over here, please. Sorry. All the way here. Here. Here, please. Okay. I don't know. Sorry, I've picked somebody. I hope it's the right person. There we go. Thank you very much. Please, if you could make a short comment, that would be great.
Okay, thank you. So you mentioned about the employment, and I think it's really about in current situation, the society is about earning the revenue from the one who pays it as the return to the labor we do. But I know, like many years ago, there was a really idealistic idea that the automated system would reduce our work and do all the laborious work and enjoy our lives. But I think this implicitly stands on the idea that people still have the properties or earnings or whatever to do the daily life, regardless of this reduced labor. But in reality, do you think are we able to accept, especially those who are in power, the idea that people are earning all these earnings for the daily lives, even though they rely on the automated machines?
Thank you very much indeed for that very interesting question. So I suppose this really raises the question of things like universal basic income, the idea that we should all, the utopian idea that our drudgery should be done by machines, yes, and we should be free to enjoy our lives. Would anybody like to tackle that question? It's a big one. Arisa, do you want to have a quick comment?
I think it's when we're talking about this, the employment and what the technology can do. The one thing is that like you mentioned, like a universal basic income. But on the other hand, when we think about especially the Japanese situation, I think we're actually facing the shortage of labor. So I think to some extent we actually are welcoming how to our tasks or our works can be taken by the artificial intelligence or the robotics. So I think the point is that it's not like our job or our work can be totally replaced by the human being, but the human being's role is to consider what can be done by human being and what can be done by machines. And that kind of management thing, I think, it can only be done by human being.
Thank you. Thank you. Yes, please, Ada.
Just a little comment to you. What can be done by human being and what can be done by machine? There is in between what can be done by nature.
Oh.
Very true, very true. But I thank you very much for raising this point of how the conversation has become one of fear of machines rather than benefit and idealized. Please, yes.
Thank you very much for your interesting talk. I was wondering if you could comment about what your opinion is on the dangers of the randomness of AI and the fact that their so-called cognitive processes are essentially an normative black box. Do you feel that this danger is a true danger?
Thank you very much indeed. So we will address, as we go forward in the discussion a little bit in a minute, the kind of future dangers. But right now, one good example of the black box is AlphaFold 2. So the protein folding problem was solved by a process we do not understand. We don't know how AlphaFold 2 does this. So do you have any quick comment on the fact that in the end, what we thought would be solved by understanding is not solved by understanding?
I prefer not to.
You prefer not to make a comment? Okay, fine. Yutaka, would you like to tackle that issue of the fact that...
Yeah, of course, there are many risks, and we have to consider about that. Actually, in Japan, we have the AI Strategy Council with Arisa, and also we recently had a group called AI Institutional Study Group that discuss about the regulation and legislation about the AI, and we made a discussion a lot about the AI risks and what can be done toward to mitigate that risk. And that trend is ongoing globally, and we have to have the international collaboration toward that respect. And to some extent, there is a misconception, misunderstanding of the recent technology. But to other respect, maybe we have to take more cautious step toward the advancement of AI. So yeah.
But sorry, Ada, you want to go?
You do it.
Well, no, I'd much rather listen to you.
So now I can say something. I was waiting. In my opinion, the next, or one of the next duties of AI is to predict which proteins can do what. So if we need to do something that is still not done naturally, can we design a protein according to what we understand to do this particular assignment?
And the question relates to this idea of, okay, as humans, if we came to that, if we managed to do that, we'd understand the processes we used to get there. In this case, we're putting information into a large language model, basically, and getting out an answer, which is, we don't know how it came to the answer. The answer is right, perhaps, but we don't know about how it got there. Does that matter?
It matters by the way we think and the reasonable way we think. But nature came to some incredible designs without studying together with us. So we have to give nature a lot of respect.
True enough.
Maybe I have one comment.
Quick.
I think, we need, I think that this kind of black boxing issue is very important, also like a transparency, accountability issue. So one thing is that technically or technologically, we need to, find a way how we can make this kind of black boxing into more like an XAI, explainable AI. That is one issue. But on the other hand, I think it's when we consider about like social risks, the problem is not about, the technology is a black box, but we actually don't know who takes the responsibility of these risks. So, consider about, when something goes very wrong or, some kind of incidents happen, and you can we made this wrong decision because this actually was the reason, But it's not like, the explanation what we want, but we want, who takes the responsibility or how to mitigate, how to prevent that kind of risk to happen, again. So I think from like social, points, we need to think about, the accountability issue as well. So I think there's a lot of way to tackle on this black boxing issue. And for my opinion, from like a social scientist, is that we need, this is also the topic of the morning session, but we need to have some kind of collaborative approach with the engineers and also like for social scientists, or more for the politicists, to tackle with this, this new challenging, but also, that brings the opportunities.
Thank you very much indeed. Thank you for the point. We have so little time to cover so much, but anyway, we're touching on things. Let's move, we have to move forward a bit. Let's use Geoff Hinton to begin that conversation. So in this podcast recording, if we could put the Geoff Hinton picture up on the screen. Now, thank you. If we could play clip 2, first of all. This is Geoff talking about whether AI will become conscious. Clip 2, please.
That's becoming very central, what it is to be human, because the debate about whether these things will want to take over is all about, do they have desires and intentions? And many people think, for example, there's something that will protect us, which is they're not conscious and we're conscious. We got something special that they ain't got, and they will never have. And I think that's just gibberish. I'm a materialist. Consciousness emerges in sufficiently complicated systems. Perhaps systems complicated enough to be able to model themselves. And there's no reason why these things won't be conscious.
Okay, and in fact, let's run straight into clip 3 as well, and then Yutaka, I'm going to come to you. So if we play clip 3 next, please. And this is about if they become...
I'm just worried by the fact that there's very few cases of more intelligent things being controlled by less intelligent things. And once they're a lot smarter than us, I don't think they'll put up with that. Well, that's what worries me, at least. Now, there's one line of argument that's more promising, which is a lot of the nasty characteristics that people have come from evolution. We evolved with small warring bands of chimpanzees, or our common ancestor was chimpanzees, and that led to this intense loyalty to your own group and intense competition with other groups, being willing to kill members of other groups. That sort of shows up in our politics quite a lot right now. These things didn't evolve. And so it may be we can avoid a lot of that nastiness in things that didn't evolve.
It's a nice thought that we could learn how to behave from
them. Yes, in fact, AI mediators are now quite good at getting people with opposing views to come to see each other's view. So there's a lot of good can be done with AI. And if we can keep it safe, it's going to be a wonderful thing.
AI mediators, maybe we should have AI moderators, I don't know. Anyway, it was interesting that he actually took a different view from Rich Roberts earlier, who was pointing out that humans kind of know how to behave towards each other. And he was saying that humans don't know how to behave each other. Maybe I will. But Yutaka, let me come to you. So will AI become conscious is one question. And then if it becomes super intelligent, will we be able to look to control it?
Yeah, thank you for asking. I think with regard to the consciousness issue, my answer is yes, that we can build the AI with consciousness, because as Hinton Sensei said, that I believe consciousness is a mechanism, and that can be clarified and revealed in an artificial way. So the AI could be conscious and they can model themselves. And that's the answer. Another question. I believe the less intelligent agent can control the more intelligent agent. That is happening all the time in the human society. Yeah, I'm sorry, but yeah. But it depends on the how reward is distributed or how the value is created. For example, if some agent is created to maximize some objective function, there could be another agent that could use that agent for their purpose. So maybe the objective function is, for example, very narrow one. The other agent can utilize that for their purpose. So it's a relation of objective function or purpose. So we can design that. And in the human society, we sometimes have the triangle control system, so that any one agent should not have the much power over others. So that kind of devices could also be possible. So, yeah.
And do you think enough work is going in currently to actually looking at how to implement all that, basically under the title of safety research?
Yeah, I don't think it's enough. We have to be, more careful about risks of AI, as Professor Hinton says always. And maybe this is not short-term, but middle-term, long-term issue. But we have to make enough endeavor to realize that kind of safety. Maybe we have more international research on this respect, and we have some governmental cooperation to, monitor the ongoing development in the companies globally. Yeah.
Arisa, would you like to comment on this also?
Yeah, I agree with what Yutaka-san said about, we are actually doing, collaborative work on the safety security issue. But when I talk with the other colleagues from overseas, I think, we need to be more conceptually talk about what does safety means, or maybe, what does consciousness means, because, when in Japanese, we call safety as anzen. Or maybe, some person or some people may think, the safety can only be applied to, the physical or financial, or maybe the national safety or the security. But it might be, dependent, even though, we use the same word, the Japanese safety might be slightly different from, European safety, because, it depended on the circumstances or situation. We're in the island society, we actually, have well-educated, but maybe in the, places with totally different situation or circumstances, what does safety mean, or safety criteria that they actually want is totally different. So I think even though, we wanted to use the artificial intelligence in, our daily lives, or maybe in like the education or the politics or other way around, I think it's, we need to, philosophically or maybe in the conceptual level, first of all, discuss about the safety and what kind of safety actually we wanted to, have. So I think this is not the technical issue or the technological issue, but it's more like ourselves, focusing on what kind of society or what kind of future we wanted to live. So that's the starting point of the question.
Do you want to comment?
I want to add something to you. Mm-hmm. The question was whether AI can become conscious. Nature is conscious. Mm-hmm. We can be upset about this point or that point, or try to change it, but nature is conscious without any human being making it. It's by nature. So all what we have to do is to follow nature in our AI.
What do you mean by nature is conscious?
We are alive. We are alive and we can take a flight from Tokyo to London. Nature is conscious. Otherwise it would fall into the ocean.
If Jeff was here, he'd say all of that, what you just said, was all very well, but actually we're in an environment where governments are deregulating AI. They're loosening the fetters. They're saying it'll stifle innovation if we impose any restriction. and that we're going in the wrong direction. And also, he'd say that government advisors were often people who had vested interests in seeing AI companies succeed. So how do you change that environment? Do you need to change that environment?
Changing the politicians?
That's another big conversation. We can talk about that at the end of the meeting, if you like. Yes, changing the politicians is one way, but would anyone like to comment? And then I'll open it to the floor for just very quick last comments.
Well, we might not directly answer to your question, but there's a kind of old saying that I really like, is that the road to hell is paved with the goodwill. So even though people are not intending to make the wrong use of the AI, or but people are thinking to make the society good or the better, but if there's a less collaboration or maybe people might think the safe society might be powered by the giant epic, the country or maybe the one of the politician. So I think what we need to do is to consider, or maybe to share the viewpoints of what does the society would like, and how we can make the governance of the AI system. And I think the world today is very becoming fragmented, and people are actually kind of entered the AI race. However, because it's entering the AI race, this is the actual point we need to think about the collaboration, or maybe to think about how we can make this AI more controllable, or maybe to make in the governance framework. So I think what we are doing currently in the governmental level, or maybe in the academic level, is very important. But I think what we also need this kind of public debate as well. Otherwise, it's not only the scientist or the politician who is making these rules or maybe using this technology, because I see that lots of people are actually using the ChatGPT today. So we are all in charge with this kind of governance of the control.
Thank you. Yutaka, very quickly.
If Professor Hinton have attended this meeting, maybe he should take the very risk side. And maybe I wanted to have the very positive side, but so I have to do both this time. But I think on the one hand, the AI advances society a lot. So we are using ChatGPT a lot, and maybe the science would even more advance with the help of AI. That's true. And on the other hand, maybe we have to have more, cautious step. And in the last dinner, many people mentioned about the Ashiroma conference, and which is a very good activity. And in the biology field, there's no accident so far. That's fantastic. And maybe same thing should happen in also the AI field. So we have to make endeavor as a researcher.
Yeah, so the Asilomar conference, self-organized by people starting the biotechnology revolution, they got together and they decided on the safety principles then and there, and that's 50 years ago. And yes, now the same thing is.
That kind of effort should be also.
We have just a minute or so, but is there somebody who wants to make a comment or ask a question, please? I'd love to hear from somebody. There's somebody right in the middle. Can we get a microphone to this person? Sorry if I didn't see anyone else. Just here. Thank you very much. So I think that pretty much the last word of this session goes to you. So.
Thank you for microphone, and thank you for nice discussion. And I have a positive opinion about the AI. If the AI is more clever, smart than human, if the government or company is organized or managed by AI, the society could become better. Of course, there is a risk, but I think the evolution of AI is a positive for human. So what do you think about the organization or management by AI?
Ada, would you like to have your institute managed by AI?
Because more clever than human, maybe.
Clever, better at management, better at handling interpersonal relations, as Jeff said, good mediators. What do you think? Very quickly.
I'm not sure that I would like to have it managed by AI formally, but in life it is. In real life it is.
Actually,
this way or that way you can look at it. At the end, AI is one of the more important factors in having my institute.
In practicality, yes, it doesn't manage you. But actually, I don't think anyone should manage you, Ada. I think you're...
Yeah, myself, of course. But the institute is larger than just me.
But in general, do you think would either of you like to comment, or both of you like to comment in like 10 seconds on the idea of AI management of companies, countries?
I think AI can manage the organization very well if given the proper objective. So setting the objective, the purpose is the human's role, I think.
My quick answer is that maybe they can, but I think if you wanted to do that in proper way, we need to change the system, because our current system is designed that this organization or maybe the government or company is controls or maybe governed by human beings. Yes, and what human can do is totally different from what technology do. So if we wanted to shift it on that way, we first need to change the system.
Thank you very much indeed. So we all need to learn from each other, basically. Wow. Okay, thank you very much indeed. We got through a lot in a short time. With your help, thank you all very much indeed. Thank you. Thank you, Hargit. Thank you. Okay. Thank you very much indeed, Arisa. Yutaka, thank you. Okay, so now we change straight over to another panel on a different subject, which is the quantum technology and the promise of quantum technology. Now, I think in this case, actually the Japanese translation for this session is the promise of quantum computing, and the English title is the promise of quantum technology. So one is focused on computing, one is rather broader on the technology. We'll try and discuss both. And for this panel, I'm joined by Bill Phillips again, who you've already met, and Akira Furusawa, who you've met, and also Mutsuko Hatano is joining us. And she has many titles, but since 2014, she's been on the Japanese Council of Science. Please welcome them all. Bill?
So where would you like me?
Oh, I don't know. What's the seating order? Let's put you in the middle.
Okay, well.
Mutsuko, do you want to be near me? And
yes. Same as before.
Thank you.
Kira, do you want to be at the end? Thank you very much indeed. So, I don't know if you're watching that, but that was the same format for this session. We have an audience in front of us. I'll try and get them to make 2 or 3 comments during the time. And we are here to discuss quantum technology. Right, where should we begin? Let's start with the quantum computing side of things. And if I could start with you, Bill and Akira. There is a question about scalability in quantum computing. The promise of quantum computing is enormous. Would you like very briefly, would one of you very briefly like to sum up what that promise is? Akira, perhaps you could tell us, what does quantum computing promise?
Okay, so first of all, in any case, we have to have large-scale quantum computer. And I think there are 2 types of quantum computers. One is optical quantum computer. Another one is electron and also spins. Those are totally different worlds. In the case of optical quantum computers, photon energy corresponds to very high temperature, like 10,000 Kelvin. So if we do quantum computing with optical systems, we are doing high energy physics. So room temperature is very low temperature for high energy physics. But in the case of electron and spins. That is very low energy. So in that case, when we use electrons and spins for qubits, we have to do low energy physics. In that case, room temperature is summer fluctuation is huge. That's why you have to go to cryogenic temperatures. So in that case, there is no scalability, I think.
Okay, but and so that you beautifully define the two approaches and the distance that they are from where we all live, if you like, at room temperature. But in terms of computing power, what problems, very briefly, what problems will quantum computers solve? If you can manage to scale them up, what will you be able to do?
So that is another thing. And I believe that we can do everything, including Shor's algorithm. I mean, so again, there are two types of quantum computing or quantum information. One is standing wave, which is conventional qubits. I mean, standing wave means the wave function stays here. And if you need many qubits, you need a lot of space. That's why you need a chip. But when we use traveling wave function like photonic system, that is totally different. I mean, we can use many pulses, and we can make time domain multiplexing. So in that case, we don't have to have a chip for making a quantum computer. For example, our machine in Riken correspond to 1,000 qubits and 340,000 gates. And it works at room temperature. Yeah. And by using that one, we will do neural network, for example. So as you know, at the moment, neural network or AI is using digital computers. In that case, analog input and AD conversion and digital computing and DA conversion and out. So it is very inefficient. But as you know, brains are analog computers without error correction. So in that case, analog input, just analog output. So it is very efficient compared to the case of digital computing. So first of all, I want to replace digital AI with our quantum AI.
Okay.
And also, on top of that, as I said, we are doing high energy physics. And in that case, the error is very limited, just vacuum noise. And that is Gaussian. So we can easily use the central limit theory to eliminate the errors. So by using such type of technology, we will do Shor's algorithm and break the RSA cryptography in 3 years or so.
Okay, so you're going to break RSA cryptography in 3 years, right? Okay, now Bill, this is the time to bring you in. So that was a lot of physics in there, and can I get you to address two questions at once, Bill? One is again this question of what will it achieve if it works, and the second is will it work?
Right. Well, the point is, the reason why people are excited about quantum computers is that there are certain kinds of problems, and I want to emphasize certain kinds of problems, that can in principle be done much faster on a quantum computer. Factoring. Shor's algorithm is an incredible achievement that showed that if you used a quantum computer, that you could factor numbers in a time that grows only like a polynomial, that is like a power, I think it's the third power, of the number of digits to be factored. Factoring is hard. Multiplying is easy. And that asymmetry between factoring being hard and multiplying being easy is the reason why public key encryption, like RSA is one example, is so effective. This is the thing that protects your credit cards from people stealing them when you make a purchase on the internet. But perhaps more importantly is the thing that protects diplomatic secrets that are transmitted between countries. So it's really important that this kind of encryption be secure. A quantum computer would make that kind of encryption insecure.
And Akira tells us he's going to break into our credit cards in 3 years' time.
Right. Now, I don't believe that, but we'll find out. The great thing about a prediction like that is it won't be that long before we'll find out whether it's right. The thing about optical quantum computing is all the things that you said about it are true, but there are other issues with optical quantum computing because of the fact that the deterministic nature. Anyway, it is something that has worked, and most people have given up on it. So the fact that you're working on it is fantastic. I'm really happy about that. But this represents a, shall we say, a departure from the standard wisdom, which is often the way you make progress. Well, anyway, what else can quantum computing do? Because it might be that it's irrelevant. We at NIST have developed, not me, but smart mathematicians have developed quantum-resistant encryption. So if everybody adopts quantum-resistant encryption, then we don't care about Shor's algorithm, except for secrets that have already been sent and can't be decrypted. Those will be vulnerable, and people will certainly buy your quantum computer in order to do that.
But presumably quantum computers aren't being developed for breaking cryptography. They're being developed for increased computing power across the board.
Well, there's only a few kinds of computations where a quantum computer is better. You see, I mean, what I forgot to say was that an ordinary computer is going to take an exponentially longer time to factor a bigger number. That is, the time required is an exponential function of how many digits for an ordinary computer, but it's only a polynomial function of how many digits for a quantum computer, and that's huge.
Okay. Thank you. So I'm going to bring Mutsuko in a minute, but because this is a conversation starting with a sort of deep physics, but I'd just like to get an example of the sort of problems that you would hope would be solved, or the secrets that would be revealed if we had it.
Okay, I'm not actually interested in breaking codes. This is something that spies are interested in, and it's one of the reasons that quantum computing became so popular. What I'm interested in is doing quantum mechanics. So if I want to do a many-body quantum mechanics problem, so that means I want to study the quantum mechanics of a system that has many individual parts, and those individual parts are correlated with each other strongly, as opposed to something where I can sort of take an average of what all the other particles are doing to think what one particle does. That's what the 20th century was about, what sometimes would be called a mean field approach to quantum mechanics. But if I need to know about the correlations among all the particles, that's a really hard problem. It's a problem that grows exponentially with the number of particles. And so, like factoring. But a quantum computer, in a sense, is ideally suited for doing those kinds of problems. In fact, it may even be a near-perfect analog to that kind of a problem. And so the thing I'm interested in doing is hard quantum mechanical problems that cannot be solved on a classical computer, but can be solved on a quantum computer, that will give me insights into how things like materials work. So, for example, one of the great unsolved problems of today is what makes high-temperature superconductors work the way they do? And there are speculations about what kind of a model we could use to describe the operation of a high-temperature superconductor. But the trouble is, some of those models, while simple to express, are impossible to calculate with a classical computer. But with a quantum computer, you could calculate those models, and you could learn whether these models are good models for high-temperature superconductivity. That's what turns me on about quantum computing.
Okay, great. Thank you very much indeed. Akira, I'll come back to you in 1 second. I just want to have Mutsuko come in on this question of what sort of thing would you like to know if quantum computing is working?
Computing. So in my other understanding, the quantum computing is extremely delicate and need because of the error accumulation of the error. So the quantum error can be essential by many additional qubits are needed, but Akira's invention is very surprised. So without any error correction, so within 3 years, so that's really fine. But I think that to accelerate maybe to use quantum realize that quantum computing, the system of the quantum and classical computing is required maybe. So for this purpose, two-way player like Nitoryu, like Shohei Ohtani, and pitcher and hitter, in Rogers expected. And however, so that a player like him is few. So the classical computing and quantum computing, the researcher is maybe the computer should be collaborate.
Collaborate, yes, indeed. Yes.
In strongly, yeah.
But okay, I was trying to get to what secrets of nature are you hoping to reveal by, if you had the power, what would you like to know?
Okay, so my message is what is life? What is life?
Good.
Yes, because what is life? And so yes, topics is future of life. So the Schrödinger, the father of the quantum mechanics.
Schrödinger, yes, he wrote What is Life? That's
yes,
right.
So what is life? And after 80 years, the Nobel Prize biologist, so I don't remember.
Paul Nurse. Paul Nurse also wrote a book called What is Life?
So published a book titled this is just the answer of the Schrödinger, what is life? But he says there's no answer, no answer. And we need to understand the maybe life science and biological phenomena. So we need a much more detail of the research and the effort. And in my opinion, the quantum technology, the quantum science and technology will contribute to clarify the life science and also such kind of the brain mechanism and also some kind of the material, new material for AI, computing and something like that I need.
Thank you, Mutsuko. So when it comes to the brain, Akira, you're producing neural networks you have the idea of producing much more advanced neural networks that will mimic the brain. Would you like to talk about that at all?
So the reason why we stick to optics is that the carrier frequency of optical carrier is more than 100 terahertz. That means we can put 10 terahertz information on that 100 terahertz carrier. So in principle, we can make quantum computer in 10 terahertz clock frequency. So at the moment, we don't, everybody doesn't think about, care about the clock frequency of AI and also other things, but clock frequency matters. So in any case, we should go to very high clock frequency to save the energy. At the moment, digital computers clock frequency is up 2 gigahertz at most. So if you want to make petaflops operation, you need many cores. That's why the consumed energy is huge. But if we can build 10 terahertz clock frequency, then so it is almost 10,000 times faster. That means 10,000 times low energy consuming. So by using such very high clock frequency computer, we want to make AI to reduce the energy consumption.
That would truly have a world-changing impact if you were able to combat this question of the energy consumption of AI systems, which is a tremendous worry now.
Yeah.
Yes, indeed. Sorry, Bill, you wanted to come in.
Well, I'm glad you brought up the question of clock frequency, because this is something that often is not discussed when people talk about quantum computing. And for example, atomic systems have pretty low clock frequencies. Traditional solid-state systems are faster. You've indicated that these optical ones could be even faster, but it goes to just the point that you made about how we need to have a hybridization of the classical computing with the quantum computing. If you're going to do error correction, then you need a classical computer that is going to do those error correction calculations. Just for those who may not know, the typical thing that happens is that when you do a quantum operation, it's not perfect. In classical computing, it's almost perfect. But with quantum systems, it's not. And the way you fix that is by a procedure called error correction, which is very expensive, both in resources and in time. And you need a classical computer to figure out what the error correction should be. And that classical computer has to be faster than your quantum computer. So if your quantum computer is really fast, you may not have a classical computer that can keep up with it. So that's one issue that is sometimes not brought up, that this can be a problem. And so co-designing of the classical computation with the quantum computation could be a really important thing for the kind of scalability that we're looking for. Now, if your quantum computer is so good that you don't have to do error correction, that's a different story. So it's just one more thing that often is not discussed when people talk about how wonderful quantum computers are, or will be.
Or will be, yes, or will not be, depending on your point of view. Yes, exactly. Thank you very much for bringing that up. Okay, but I'm going to come to the audience in a second. But Mutsuko, I just wanted these are the near or far future applications of quantum computing, depending on which side you land on. But there are now. There are very real applications of just quantum mechanics, which Bill has already outlined in some of the discussions already today. But you work with quantum sensors yourself. Yes. So would you like to tell us a little bit about that, just very briefly?
Quantum sensing is have already implementation of the society. Quantum atomic clock is a standard of the clock. And so now we are trying, my research focus on the quantum sensing. So because of the, with higher sensitivity and multimodality of the physics and variable, and also the dynamic ranges are very wide. And so my goal is to realize quantum life science.
Quantum life sciences.
Or so for life science, the emerging field between quantum physics and life science, and maybe so the purpose is, I believe the quantum phenomena in the life science and in the brain or cell and nerves and hierarchical application of the life science. And so the quantum phenomena in the life science and detect the quantum sensing and then analyze the quantum computing is my ideal system of the quantum.
So what exactly, give me an example of something you measure and something you find out through quantum sensing.
Quantum sensing of some brain activity and so on.
Of what activity, sorry?
The brain.
Of brain activity, quantum sensing of brain activity, okay. In order to find out what?
In order to apply something like the relationship between the brain and emotional things and so on. So long-term targeting, but...
That's the secret to everything. Bill, did you want to?
Well, I just like to bring up something much more mundane, but is coming to reality even as we speak. The point you brought up about atomic clocks. One of the troubles with atomic clocks is that the very best ones have very few atoms because the interaction between the atoms is often a problem in the accuracy of the clocks. The trouble is if you have very few atoms, then the signal-to-noise ratio is not very good. And you have to work for a long time. You have to look for a long time before you realize the high accuracy of the atomic clock. You may have to average for days or weeks or even months to achieve the kind of accuracy that the atomic clock is capable of. But if you can figure out how to add just a few atoms together so they don't interact very much, and then do some magic where you quantum entangle the atoms. Now we haven't described what quantum entangling is, but it's something that is part of the sort of 21st century quantum mechanics that is so important in quantum computing. That kind of quantum sensing is an important feature that we're already taking advantage of. So it means that you could make these atomic clocks work better, faster. Same thing is true of, for example, detecting the level of very dilute pollutants in the air. Hard to see because the signal's noise isn't so good. But if you quantum squeeze the light has, as you mentioned, Gaussian shot noise, unless you do something to fix that. And we can do something, again, it's a quantum phenomena, where the light has less in the way of fluctuations than would be the case with natural light, the kind of thing that comes from a laser, for example. We would do something more sophisticated, and then that light, because it would have less fluctuations, would be a better tool for detecting very dilute pollutants. So these kinds of quantum sensors are really near term.
Thank you.
People are making them now.
Thank you very much indeed. Did you want to comment, Akira, before we go to the audience? Do you want?
Speaking of squeezed light, of course, for our quantum computer, for entanglement source, we are using squeezed light. So in any case, quantum computing is a synchronization of quanta, right? And that synchronization is called entanglement. So in any case, we have to use entanglement for quantum computing, and our resource is squeezed light. And again, it is deterministic, not conditional.
Thank you. Let me see if there's, yes, please, there's a question here or a comment here. Could we have a microphone, please? Thank you. Hi, thank you.
Hello. Sir, very recently this Microsoft developed topological quantum qubits, which is more robust as compared to conventional qubits. And they use Majorana, right? Majorana particles. So how this Majorana and the topological can change the world of this quantum computing? Can you tell us something about?
That's a question, but this has become a conversation between physicists. Go for it.
Well, the problem is that the whole problem of topological qubits, which there's been a recent demonstration and publication about topological qubits, has turned out to be rather controversial, which I guess is what motivated your question in the first place. So So the idea is that if you can make a topological, and I haven't said what that even means, a topological qubit, because of the way it's made, it is exceptionally resistant to decoherence, which is the enemy of all quantum computations. And then the idea is that if you can make a quantum computer that works with topological qubits, then you may not need to do error correction at all, or you may need to only do it very little, which means that it won't require a lot of resources. So people get really excited about topological quantum computing. The PR, that is public relations output about these topological quantum bits, is rather different from what you read if you read the paper. The paper is very clear and conservative about what it claims, and the press releases say this is going to solve all our problems. Well, we'll see. So I would say that what has been happened is that they've demonstrated a topological quantum bit. That's great, but it's only the first step in a very long journey to make a quantum computer. So we'll see, but I'd love to hear what anybody else thinks about this.
I'd love to. Yes, please,
I have
Akira.
a comment. You have to distinguish between physical qubit and logical qubit. Just one physical qubit, you cannot make any quantum error correction. For quantum error correction, you have to make logical qubit that is entangled state of many qubits. So I'm not quite sure about that Majorana qubit, but if you want to make a quantum error correction, you have to use many physical qubits to make a single logical qubit. On top of that, for topological quantum information processing, you have to make magic states. So it is rather tricky state, and I think it is really hard to create at the moment.
Thank you very much indeed for the question. I think this conversation illustrates one of the challenges that quantum technology faces, in that, as you mentioned earlier, Bill, when Einstein came up with his theory, people were saying there are only 3 people in the world who understand this. This is a very in-house conversation. It's very difficult for people outside of the field to come anywhere close to understanding anything about this. And so all they can understand is the promise, the oft-talked of promise. And the promise, like many things, is often, another good example, of course, is nuclear fusion, where the promise of nuclear fusion is always there, but never realized as yet. In this case, we may be realizing the promise of quantum computing soon, but how do you have that discussion with the public about a topic that is so hard to get any understanding of?
Well, I noticed that you've very carefully avoided using the term hype, which I'm afraid has been an ongoing characteristic of quantum computing. There's a lot of over-promising, in my humble opinion, that people say quantum computing is going to solve the energy crisis, it's going to solve the climate crisis, it's going to create new pharmaceuticals, all these things that quantum computing is going to do, that is pure speculation at this point, in my humble opinion, that it's wonderful to dream, it's good to dream, but to claim that quantum computers are going to do this when at the moment it's highly speculative, I think that's dangerous. Because if you promise these things for too long and don't produce, then the people who are giving you money, the minister who used to be here in the front row.
You see, Mutsuko making decisions about such things, but yes, no, yes, exactly.
These people may become disheartened with these overpromises and change their attitude about funding. Quantum computing is going to be fantastic. It's already fantastic. And I don't think we need to overhype it. Now, this isn't really answering your question. How do you talk to the public about it? But I think the first thing is you do it honestly. And I think there's been a lot of failure to be completely honest about the promise of quantum computing. Explaining how quantum computers are different and why they're better for some kinds of problems to the general public is not easy, because it's hard to understand these features if you don't know something about quantum mechanics. So just yesterday when we were at the museum, one of the questions I was asking of the museum exhibitors were, how are you going to deal with the problem of quantum mechanical superposition, something essential to quantum computing, but hard to describe to someone who has not been immersed in quantum mechanics for years. The idea that something can be in two places at the same time. That sounds ridiculous, and it is ridiculous, but in a certain sense it's still true. And explaining that in a short period of time is simply not easy, and I don't know the answer to that. If you're willing to sit down and listen to me lecture for an hour, I think I can give you a pretty good idea of what that's all about. But if you want the elevator speech, the 2-minute version of why quantum computers work, that's hard, and I don't know how to do it.
Well, that is a problem, isn't it? And quantum science isn't alone in having trouble in having honest, or at least a straightforward discussion with the public. It's always a problem, but certainly in 2 minutes it's very hard. And one understands why journalists, etc., will just go for the hype. But I should let Akira and Mutsuko both comment on this. So would you like to respond to that?
Yeah, it's really hard to explain what is quantum mechanics. I don't know, honestly. Even Albert Einstein could not understand quantum mechanics, so I cannot understand quantum mechanics. That is my answer.
That's a lovely, honest answer. That's a good starting point. Thank you. Mutsuko.
I think that this year is a chance to understand the quantum because of the 2000, as you mentioned in this morning. This year, 2025, in the International Year of Quantum Science and Technology, and recognized 100 years of since Heisenberg published the quantum mechanics paper. Okay, but my understanding, the 100 years of quantum is just starting.
Yeah, that's right.
Just starting, yes, indeed. Okay, another quick comment from the audience. Would anybody else like to say anything? Don't have to, but do I see a hand? I'm sorry if I'm not seeing you. Shout if you are holding your hand up. Yes, great, thank you. Hi again.
What, in your opinion, are the largest problems that need to be solved to move quantum technology and quantum computing forward?
Akira, what's the largest problem? Very briefly.
It's really hard to tell. Of course, in some sense, everything is a problem because I cannot understand quantum mechanics. But a good thing is that I can enjoy quantum mechanics. So I can't not answer the question. So everything, but I can enjoy.
Well, as you point out, the fact that we don't understand quantum mechanics does not prevent us from making quantum computers. There may be some deeper questions about quantum mechanics that quantum computers will elucidate. But to answer your question about what the biggest problem is, it depends on what kind of quantum computer you want to make. If you want to make a what's it called? A NISC machine. This is a small scale, noisy machine that you don't do error correction on, but you can still do some simple problems. Then the big problem is making the decoherence small enough that you can do a decent sized problem without doing error correction. If you want to do a fully error corrected problem, the big step that I think needs to be made is to make error correction so that you have you control the decoherence. You see, the thing is, if you do this process of error correction, which we haven't described at all, it requires lots of qubits, as you've described, to make this a logical qubit. To make that logical qubit have a lifetime before it decoheres, and we haven't really talked about what decoherence is, but it's the enemy of quantum computing. Nobody has demonstrated to make that time so long that it doesn't matter. That's the challenge for making that kind of quantum computer, to make the lifetime of a logical qubit be so long that it's longer than the time of your computation. If that's not true, we're not making a proper, fully functional, error-corrected quantum computer. And so far, what people have shown is that you can extend the lifetime by a factor of a little. And so we're a long way away. That doesn't mean I don't think it'll happen. But that's where I see the big challenge is.
Thank you very much indeed. We're coming to the end of the time. So actually, both in this session and the session that went before it on AI, there's a fascinating conversation emerging about progress in the face of some lack of understanding in quantum, whether it's in quantum science and quantum computers, or whether it's in what actually happens within the black box of AI, within the deep learning networks. It's an interesting thing to discuss. Maybe it's a future panel, but for the moment, I need to finish by having you two finish where we started. Akira, you think that we're going to have a quantum computer that's functional and scaled up in 3 years' time? Yep. Okay. Bill, what's your bet?
20 years.
20 years. Mutsuko, would you like to?
15 years.
15, very, very wise, judicious, coming in the middle there. Very sensible.
And by the way, I have a bet with colleagues about when it'll happen. And the time scale for the bet is 20 years. And I'm betting on the side that even in 20 years, it won't be ready.
Ooh.
But what I find is when I talk to people who are experts in the field, about half of them go on the side of no in 20 years and half yes on the side of 20 years. So I think 20 years is a good number.
And what's the wager?
Okay.
What have you
The
got?
wager is that we're going to put up money and give it to some professional society to keep and accumulate interest. And then after 20 years, when I'll be dead, the money will not go to my heirs if I win. The money will go to a prize for people studying fundamentals of quantum mechanics.
Fabulous. Lovely. That's beautiful.
I have a comment. That question depends on the definition of...
Yes. Yeah. And I have a very specific definition.
Scale.
Can that computer factor a number that cannot be factored by a classical computer of that era in 1 year? So you give a classical computer a year to factor a number, and the number that's big enough that it cannot do it in 1 year, 20 years from now, when computers will be faster.
Within 1 year.
The question is, will a quantum computer be able to factor that number?
Fair test.
Definition.
So I think that's a clear. I don't like factoring, but it's very clear what the problem is.
I think so too.
Okay, I think this conversation is going to continue outside. Thank you.
Next, we have the Wagaki ensemble Mahora. They are a group of professional musicians formed in 2010 by graduates of Tokyo University of the Arts. Performing with traditional Japanese instruments such as koto, shakuhachi, shamisen, and kokyu, they share the beauty of classical music in modern settings and are gaining recognition both in Japan and abroad. Please enjoy.
very much. Thank you very much indeed. So we're shortly to come to our last main panel of the day, and then there'll be a quick closing reflections from the Nobel laureates. I'd like to say hello to a bunch of students in the audience. We're joined by many of the participants in the forthcoming HOPE meeting that JSPS organize every year, students from around Asia and Africa. If you're in the HOPE meeting, please shout hello. A quiet hello, a very, very modest, demure hello. Hello to you all. For this last panel, we'll be thinking about what we need to do to get the future we want from science and technology, and that, of course, has been talked about all day. But now we'll focus on it more. And for this, I'm joined by Richard Roberts, who you'll have already met, Nobel laureate. Half of you will have already met Joe Ecker from the Salk Institute in the genomics panel, and also Eva Olsson from Chalmers University of Technology in Gothenburg in the sustainability panel. And joining us for the first time is Shunsuke Managi, who is a professor and chief sustainability officer at Kyushu University. Please welcome our panel. Thank you very much indeed. So there's been so much discussed, so many different realms of science and technology, and all of them, their impact and the potential challenges surrounding them. And we're all concerned about how they should find their best place in the public sphere, in society. I thought it might be interesting just to take one example and think about how to have the best possible outcome from it and the best possible conversation with society, because so much is dependent on the inclusion of many people in the conversation. So I thought we might focus on GMOs, genetically modified organisms, as a starting point. Now, Rich, perhaps I can begin with you, and then we'll move on from there. But Rich, tell us why it's incredibly important in your eyes that there is a good reception for GMOs.
Well, the real thing is there is a tremendous amount of hunger in this world. You know, there are something like 600,000 children are stunted because they didn't get good nutrition when they were young. There are many ways in which we can solve these problems, and GMOs provide the perfect answer. We can improve plants. We've been breeding plants for years. We can improve them now in much better, much more accurate, much faster methods than we ever used to be able to. And we do this using the method that is called GMO, genetically modified organism, in which essentially we take a gene, we know what it does, and we put it into the plant at a location where we know what it is, and then make sure it's not caused any problems. In this way, we can improve yield, we can improve nutrition, any other things that we want to do. And unfortunately, what happened is that when Monsanto first tried to introduce a GMO plant into Europe, Greenpeace decided this was a very good thing for them because they didn't like Monsanto particularly. And so what they did, they came out and claimed, oh, these could be dangerous. Let's not do anything about them. Let's stop it. And this was against Monsanto, not against GMOs especially. They just chose GMOs as the way to do it. And in the process of doing this, they have scared people around the world, deliberately scared them. They went to Hollywood to make movies that would scare people about GMOs. They put out an awful lot of propaganda on social media and elsewhere to scare people deliberately about GMOs. And why did they do it? They discovered that after they came out against GMOs, the income that they derived from donation tripled. They got 3 times as much money as they'd been collecting before. And now, 30 years on, we know that GMOs are safe. In 30 years, there's not been a single accident with GMOs, not one. So why doesn't Greenpeace say, oh, you know, these are okay? Could it be money? Could it be the power that they've managed to achieve in Europe? And could it be that they really don't care about the rest of the world. You know, they've been opposed to golden rice. Golden rice is a wonderful GMO. The grain of rice does not normally carry beta-carotene. Beta-carotene is the precursor of vitamin A. Two scientists, Ingo Petraikas and Peter Bayer, figured out how to make beta-carotene be produced in the grain of rice. It makes it a little yellow, called it golden rice. Greenpeace have spent so much time and effort against this, and in the meantime, something like 25 million children have either gone blind, died, or suffered immune defects because they were not getting enough vitamin A.
Rich, you've beautifully set out the problem. Thank you very much indeed. And you've also illustrated why this is a good test case. It could be any science and technology we're talking about. There is a public perception issue to be confronted here. But to be fair, genetically modified organisms also include, for instance, genetically modified humans, which do scare people and have been created already. So maybe I can turn to Joe now, a geneticist in plants and animals at the Salk Institute. Would you like to extend the comment?
My greatest fear about GMOs is that the technology won't be utilized because of such fear and misunderstanding. And the current environment in Europe, for example, is not based on science in terms of GMOs. That it's something somewhat arbitrary. That is, you can go in now with new technology. You don't need to make a transgene anymore, like Ingo and Peter Bayer did. You can edit the existing genes in the plant to increase the amount of beta-carotene so that you don't actually have to make a GMO. But in Europe, you're restricted to arbitrarily 20 edits in the genome. If you go to 21, it becomes a GMO. It doesn't make any sense. If you take two plants of a crop that have been grown together, that are siblings, there are more variants between their genomes than the 20 that you want to edit. So it doesn't make any scientific sense. And I think what we need to do is convey, we haven't done a good job at conveying the power of the technology and how it could benefit. The example Rich gave was benefit to the farmer, benefit to the company of selling more, herbicide or other products. But so the community didn't see a benefit, and therefore when you raise a red flag, it's like that doesn't benefit us. So why should we support GMOs? But there are clear reasons, and the best example is the vitamin A. That rice was over 20 years ago, and it's the only place that's grown at any significance is the Philippines, and even then, it's not it's not grown at levels that are really useful for the population.
Well, it's actually stopped completely at the moment because Greenpeace filed a lawsuit there to stop it.
Thank you very much indeed. Shun, you're an economist specializing in the economics of sustainability, but from a behavioral economics standpoint, how would you tackle this question?
There are many different types of the empirical evidence on the GMO product. So we can say if the perceived benefit exceeds the risk or cost, people buy or people admit. And the key question is how the scientific knowledge or scientific trust increase our perceived benefit. And the question is yes, from the many different products of GMO. So actually it's good. So the more the knowledge people aware about it, it's actually solve the problem. But the different problem will be the risk. And more the knowledge doesn't necessarily reduce the risk people perceive. So actually the certain people, or maybe on average, those people who don't, people thinking it's a risk, they don't change their opinion, even they become more knowledgeable or not. So those empirical evidence tell that for the society to encourage more better use of the new technology, we need to have a good scientific or ethical committee so that it can tell how good it is and what will be the people can misunderstood and what will be the potential risk to the societies.
that's good if people trust those committees. I mean, the thing is that people seem to want to find risk. I mean, if we move away from Greenpeace's role in this, I mean, there is a general societal concern about what science will do. GMOs are a great primary example, and that's why we started with them. But how do you tackle, from a behavioral economics standpoint, the population's feelings about these things?
Yeah, population's feeling is a good point, but usually what's a behavioral science tell is if it's from the starting point is a very important part. If we perceive this supposed to be the good, then the product sold well, and if in the starting point people have a negative feeling, usually it doesn't solve the problem much. So when the new product is coming out, the industry or scientists need to be more cautious on the first point of the selling or providing the product. And if they couldn't do well, probably maybe because of non-governmental organization or committee, then they have to be more careful on providing many different type of evidence. And it's same as the vaccination for the COVID-19. There are many stories saying that this is not good for the health and this is good. And certain people cite different type of the journal article, which is sometimes not good, sometimes good. So people don't have a pretty much clear answers, because there's no overall argument or committee that tells this is a kind of risk. Many other people say this is really true, or other people say this is really bad. And those people don't seem to change their opinion after all, even after 3 or 4 years.
Mm. Well, it's a problem confronting us in many spheres. Eva, would you like to jump in on this?
So when I hear these two examples now, with the GMO, but also with the vaccine for COVID, it's an example of that we can achieve. We have the capacity, us as humans, we have the capacity of finding solutions. And I think it's important that we actually have very good education, because we are flooded with information, and there is misinformation, but there is also true information. And I think that each individual needs to have the capability of understanding what is the true facts in order to make their own decision, not to rely on other organizations as we had in this example. So I believe that education is key for future.
Hmm. It's a beautiful scenario that you can educate everybody, but there's a long road to go down. People are hungry for education, but providing it is hard. Yes?
Right. You know, one of the problems is social media is busy taking over from the educational system, right? People spend all their time looking at social media. You get hooked on it, and all you do is amplify whatever was the first message that came your way. And for me, I think social media is terribly dangerous, very dangerous.
But do you see any prospect of that changing? I mean, that's the thing.
Yeah, for that, again, probably in that point, education might be a help, because now, over the time, people seem to understand the fake news from the social media spread faster than the true news. Mm-hmm. So once more people are educated, they can have different judgment. So it encourages us to read more books, and more books says we have many different evidence, and our knowledge can connect each of the dots each other. So more the education helps those different community to understand and make a better decision in the longer term.
Joe, do you want to jump?
I was just going to say, maybe engaging the public at an earlier stage in when there's a new technological development by having, the committees have representation of the communities that they're planning to serve. Do they want this? Do they think this is a useful technology? And have input at a bit earlier stage than, hey, we've got this thing here, and how do you like it?
Mm-hmm. Well, that speaks to the responsibility of developers, of scientists, to speak at an early stage. But I suppose everybody has a responsibility in this. This is the thing. It is a mutual responsibility to push this message out and to educate.
Yeah, Rich has been an advocate, for genetically modified organisms. Another example is the folks that are developed CRISPR. Jennifer Doudna has been doing a lot of public communication about this. So I think, handing over technology that you believe is useful to the community without explaining it to them at some point is going to backfire, like what happened when the seeds appeared from the ship that came to Europe that had genetically modified soybean. Right? They didn't want it. They made it send it back. And so I think if you engage the community at a much earlier stage and they feel like they have a voice in it, then it may be easier to get it accepted.
Please, Rich.
I think one of the problems there is that many of the groups that are against science of one sort and another, they don't rely on grant funds in order to make their case. We as scientists, we don't have the money to go out and engage socially in the way that the others do, and so we get beaten down rather too easily. And it is difficult to get over that. We have 179 Nobel laureates have all signed on saying GMOs are good. Greenpeace won't talk to us. They refuse to talk to us. It is very difficult when you're going against something that has become so scary in society to say it's okay.
But those Nobel laureates are an important voice, as is, for instance, potentially the committee of ethicists and others who state what's important. And Shun, I'd like to come to you, but I'm just going to say that perhaps it's the community out there, it's the young people, it's the people who are on social media who are really going to be the voice that might change things. Because if people don't want to listen to authority, they might listen to each other. But anyway, yes, sorry.
Yeah, for the issue for the power, probably scientists doesn't have enough power to convey the message to the public, but we can get a good help from the different industry or partially some of the international organizations such as United Nations. For example, what I do for the UN environment, we do write a report together with them. So the budget is not that big, but we do summarize everything together. But we can say what's going to be the future better index to judge the future is better than now. So in the longer term process, those kind of voice making from the international community using the writing part from the academics can be a help.
Eva, I love the point you made about these are success stories and they're hopeful, and that talk a bit more about that, about the importance of hope, if you like.
Pardon?
The importance of hope.
Well, I do have hope, because I think that basically, in the end, there is a positive, there is something positive within us all. And when I think about these things, I go back to Alfred Nobel. And I realized that already when he wrote his will, he was very clever in not only taking a prize in one area like in physics, but he actually made it in chemistry, in physics, literature, peace. And he had the insight that we should work for the benefit of humankind. And if we look at what has resulted from that is something where we have groundbreaking discoveries and inventions actually working for the benefit of mankind. So I think I learned a lot from Alfred Nobel and the way that he was thinking about the future. I believe that we have the young generation today where they have the power of making a difference. And I understand there is a problem, especially with social media. But I also believe that if we learn to educate, but also communicate in a way, in a similar way, to get our messages through, I think that we can change. And I know that some things go very quickly, other things go very slowly. And the Nobel Prizes are examples of that. But I believe that if we formulate what is important for us, we have the capacity of going there.
Thank you very much indeed. Joe, I mean, I would like to concentrate a little bit on this question of authority versus the kind of the public conversation, because the public conversation is in some ways in the world taking over. And therefore, does one not just have to embrace it in order to ensure that we go in the direction we want to go? Is it any more the case that you can simply, if you like, talk down and say, this is how it ought to be?
Well, so this is, I think, it's innate in science, I think, for when you have the knowledge that this is safe, that you proselytize, you say, this is fantastic, you got to accept this. But you have to listen to the other side. You have to put the good with the bad, or the potential with the risks. And that way people say, oh, this person's not selling me the rotten fish, right? They're actually honest about the benefits and the potential downsides. And I think that probably that hasn't been done enough, and that we tend to say, wow, wasn't that really a great thing that I just developed? And, without talking about the possible risks.
Yeah, because exactly, because isn't it, for instance, the same with AI, that the AI is affecting the lives of everybody, and yet most people aren't even beginning to be included in that conversation. And where does that leave them? It just leaves them feeling that it's delivered to them. But somehow, and it's uncomfortable to include people, but somehow inclusiveness has to be part of it. But sorry.
Yeah, I would sort of comment on what you were just saying. But if you look at the regular news media, which is where an awful lot of the population get their information from, the news media like to take any controversial story, show both sides, and pretend they're identical. This is a problem. Okay, if one side is clearly correct and the other side is not so correct, why would the media pretend that both are correct? And I think this is a source of misinformation for a lot of people.
But just to challenge you on that, they do in almost all cases, but there are certain cases where they decide something is correct. I mean, for instance, in the Western media in general, the Ukraine war has been an example where it is reported as if there is one correct side. So the media does come down on a side when they really feel pressured to do so or believe in doing so. So in science, they could do the same.
Use that as an example of controversy. I think the solution there, pretty obvious who caused the problem.
Absolutely, absolutely. Okay. But that's the point. It is obvious. So the media doesn't always have in science to represent one side over the other. Sorry. Yes, Shun.
I think probably two decades ago, many people thought media was on the average or mean expression. But nowadays, people tend to think media is biased already. So in the long run, it doesn't really matter whether they are telling the truth or not, because many of the readers tend to understand this particular media is more right-hand side or left-hand side. So I think what you said is like the education helps them to understand what's this particular information from the media would be useful. So it's going to be kind of so difficult to convince the media people, as you said about particular non-governmental organizations, but more communication to the public in the many different occasions by changing the discipline from the one biology to the chemistry or economics. So those interdisciplinary communication to the public will be useful more over the longer run. Because in the shorter term, usually we cannot change much, but in the longer run, it's going to always be changing. Like the example from the IT information technology, or maybe nowadays AI. The short-term productivity from the industry is not so much, but in the long run, economic growth will be the huge one. So we are always expecting the longer run communication to the public, so not giving up in the shorter time.
Thank you very much. Okay, last comments. We're running out of time. Joe, do you want to?
Well, I'm just in this general acceptance of things. It's interesting that, if someone develops a medicine that is gene therapy, which is genetic modification, and it's going to save their child, they're all for it, right? So there's a kind of this disconnect between technology that can help a human disease versus any other fantastic use. And so it's interesting to me that, you don't see a lot of people saying, I'm not going to give that medicine to my child because it's GMO. It's insulin that was made in an E. coli or something. And that's fine, right? So there's really an education that I think individuals have to educate themselves about these, whatever new technology it is. And the media doesn't help in some of this. Sometimes they sensationalize it.
Okay, thank you very much
We
indeed.
also face a case in the US where the government is not helping. RFK Jr. is against vaccines. I mean, what is going through his head? It must be this worm he's got in his head that is causing problems.
There's a whole conversation to be had there. Ava, I'm going to give the last words to you because I'm relying on you to say something positive and hopeful.
I believe that there are solutions. I know that there are problems. It's not that I'm closing my eyes for that, but I believe that there are solutions, and I believe that in the end, the good will win.
Thank you.
And I believe in Alfred Nobel and his ambition to make the world better.
Thank you, Eva. Thank you all very much indeed. So, Rich, I'm going to keep you on stage. I'm going to say goodbye to our other panelists, if I may. And we're just going to use the last few minutes to bring all our Nobel laureates together. So I don't know if there's a seating plan, and I think we need one more seat, but I think I'm going to be joined by all the people you've met earlier during the day, although I think Svante Pääbo, who arrived by plane just before his talk, I think may have needed to go and rest a little bit. But I think we have everyone else. So
I'll go and sit at the back.
You go and sit at the back. Please, if you could all join me. Yes, please. Hello. Bill Phillips. Andrew Fire.
Thank you for the golden rice thing. That, the golden rice is such a clear picture.
Wait for it.
And the fact that it's completely available to anybody. No.
Thank you, Ada.
No charges.
No charges. I mean, it's just a crime.
Third seat. Okay.
Ada Yonath, Ben Feringa. Welcome all. Thank you very much indeed. So we have this tradition at the end of our dialogues of bringing you all together just for a very few minutes, and it's such a short session. It's just to reflect on the day. We've called it reflections on creativity, because I suppose that's one of the things that unites you, that you've all found creative approaches to solving problems in science. And when I say unites you, I think one thing that I always like to point out at a moment like this is you've listened to these laureates today. One might be forgiven for thinking that Nobel laureates are just one sort of scientist, but I think the diversity of the personalities comes out beautifully in a lot of you, so it's very nice to have you together. So, who would like to start by reflecting on the day or on creativity? Be bold. Ada, you've been given the floor.
I don't know what to say.
Okay, then we'll come back to you. That's fine. Ben.
Yeah, I enjoyed so much, and I want to thank all the young people here for participating and you for making this possible. I talked in the break with several students and young scientists from which are participating, and I was really getting more energized, enthusiastic about the discussion, the question, how should I proceed? What should I do? How to make a career, How can I contribute to these topics? And I must say this reflects exactly what I experience and why I enjoy to be at the university, with all these young talents. And every time, of course, we run a program over many, many years. Yeah, and we think as senior scientists that we are very clever. And then suddenly these young talents come in the lab, fresh mind, and they are extremely creative, and they look from a different perspective. And they say, did you ever try this? No, I have never thought about that even, you know. So thank you all for bringing this excitement to us and the creativity that helps science forward to shape our future.
Beautiful. Thank you very much. Let's go down the line. Andy.
Yeah, I mean, I really echoing what Dr. Feringa said. I mean, I think for the young scientists here, one of the really significant lessons will be that nobody ever told us to be creative. We just sort of decided our own we had an opportunity to be. And some of us have, in our different ways, been leaders in the scientific community or in the community at large. And nobody ever said that either. And so at some point, our generation will be off retired and doing wonderful things at age 120, and you'll be the leaders of science. And no one's going to tell you at any point, now you're the leader. It's something that you'll realize that you have an opportunity, in some cases a responsibility, to carry out. And I know you'll do very well with it and make a better world. So thank you in advance for that.
Thank you. Thank you.
Well, I'm going to take issue with that. Because when young people come into my group, one of the things I tell them is, your job is to be creative. I don't have a plan for what I want you to do. I want you to tell me what the next exciting thing is and how we're going to find our way to that next exciting thing. But I also want to pick up on something that Adam said about how you might have some conception about what a Nobel laureate is like. And one of the common conceptions, I think, which is completely false, is that Nobel laureate is just something special. Now, some of them are. You know, when I think about, since this is the International Year of Quantum, how Heisenberg goes to this island off the coast of Germany to deal with his allergies, and in 10 days comes up with quantum mechanics. How does something like that happen? I can't imagine that kind of creativity. But yet, my whole career has been doing things that are creative in some much smaller way, some much more pedestrian kind of creativity. And both kinds of things are important. You don't have to be a Heisenberg or a Schrödinger or an Einstein or a Bohr to make a contribution to physics to end up, I mean, let's face it, getting a Nobel Prize is an awful lot of luck. But that doesn't mean that you can't contribute to this marvelous adventure that is the progress of science. Now, one of the things that people often ask is, what does it take to make a creative environment? I think it takes being in a place where the kind of thing you're doing is valued. That learning something new about the way nature works is something that your organization values and that is willing to embrace, that they're not going to say, no, we're not going to handle this golden rice because it's GMO. We're going to love this because it's a new way that we hadn't thought of for solving this kind of problem. You need to have that kind of environment. Of course, you know, people are creative in every kind of environment. So there's no easy answer to what makes a creative environment. What I'd like to see is organizations that are open, that say to their people, not, I expect you to accomplish this in the next 8 months. No, I expect you to come up with new stuff.
It sounds like a beautiful, nurturing world you have. And you probably got yourself several applications from the audience in the last 2 minutes.
Okay, I would also like to follow up on luck. Luck is unbelievably important. You know, when I made the discovery for which I won the Nobel Prize, we were trying to do something totally different. It didn't work. It was a failure. And then we looked to see why it failed. And nature was trying to tell us something, and we discovered what it was. And that brings to another point, is that failure is really important, you know. Experiments, they don't have to succeed. Right? And if they don't succeed and you do them right, nature's trying to tell you, here is a discovery to make. So I love failure. I love it when students come to me and say, hey, I did what you told me to do. It didn't work. Maybe there's a discovery there. This is excitement. But the other thing about creativity is that the education systems in many countries seem designed to knock the creativity out of children. All young children are creative. Yeah. And they go to school and it's knocked out of them. So that is not a good thing. And then the other thing for me personally is I've always felt I don't like people telling me what to do. If someone says, oh, you should do this, I want to do the opposite because I think they thought of it, it can't be that interesting. I want to learn about it. And so make sure that whatever you're doing as a student, don't let someone tell you, oh, don't do that, do this. If you think that doing this is wrong, do what you think is right.
I think that not wanting to be told what to do is universal among laureates, and you should try working with them, I'm telling you. Ben, I know you wanted to come back on some of the comments. You wanted to just extend some comments, and then I'm going to come to you. So I think you wanted to make a comment on the back, or you were just nodding in agreement with everything. Did you want to say something else?
No,
you did?
I just wanted to say that I fully agree with these gentlemen. And don't be afraid. I know all the young stars here. Don't look at the old chaps all the time, eh?
Right.
Because Van 't Hoff, the first Nobel laureate in chemistry, was 23 years old, only, your age, 23 years, when he did his major discovery about the three-dimensional picture of carbon, the three-dimensional model, that completely changed the way we look at molecules. 23 years, don't forget that.
Now you've just depressed the whole audience. They're thinking, oh, I'm 23 and I haven't done it.
Not my age.
Ada, last comment goes to you.
Last comment. When I was a young student, a young scientist, we looked at how things are working, how nature works, how nature achieves what nature needs. Now we know, not all, but a lot of it. What we're looking, or should look now, is why is it so? Why did nature go this way, and not that way, and not that way, and not in a way that we couldn't think about? So I think that, in my opinion, what to do now is to understand why things are performed in nature in a specific way and not in another way.
Listening to nature seems a good point to stop. Thank you. Bill?
I want to emphasize what Rich said. I give talks to all kinds of groups of people, and one of the people I love the best to give talks to is a kindergarten class. I go in there and I throw liquid nitrogen on the floor, and it boils, and there's a cloud coming up, and every one of those kindergarten kids is down on their hands and knees trying to see what this marvelous stuff is. If I do the same thing to a class of 16-year-olds, they're all jumping up and getting on their chairs to avoid whatever this horrible stuff is. The ones that don't are the ones that I'm guessing are going to become scientists. And this is just what Rich was saying. So creativity, you got to keep that spirit of being a 5-year-old.
That is a good point to end on. Thank you all very much indeed. And thank you to the audience for being here with us all day. You've made it possible by being here. We do it for you, and we're very grateful for your presence. So I'd just like to thank all our participants and particularly our laureates here. Thank you very much indeed.
You pegged it. You really pegged it.